Okay, so anyway, let's get started. Again, thanks everyone for coming this early to being able to fit in this room. Definitely next time we'll just consider having a much larger room than this. But anyway, today's workshop, we're going to talk about visual generative modeling, what's after diffusion. And I'm Tianhong Li. I'm a postdoc now at MIT, working with Professor Kaiming. And um, I'm also a co-organizer of this workshop. I will be mainly hosting this workshop today. By hosting, I'm just saying introducing new speakers. Um, and I also, again, I'd like to thank all the other organizers, Yilun, Tianyuan, Tim, Shuang, Arash, and Kaiming, to make this workshop happen. So first of all, like why we're organizing this workshop, I guess that's the most important question I want to ask. And we all know that generative models are definitely one of the most hot topic in today's no matter computer vision or any area in machine learning, and can be seen by this attendance. And now I guess everyone knows that diffusion models works pretty well in modeling, it's a continuous signals or visual signals. But as researchers, we always want to challenge common wisdoms. So we don't want to just follow what diffusion model is saying is good, but instead we want to say, okay, what's the problem with diffusion, and what can be the next challenger for diffusion models? So that's the point of today's workshop. And in today's workshop, we will invite mostly or entirely invite top researchers to discuss about what's after diffusion in visual generative modeling, this topic. And you will learn the most frontier techniques and also the insights from both researchers from academia and industry about what's after diffusion models. Okay, so briefly speaking, in today's workshop, we'll mainly discuss three topics, or in general, I can group all of our talks into one of these three topics. So first of all, we will discuss what are the limitations of the current diffusion-based visual generative modeling methods, and also many methods we can use to overcome them. So we all know that other models is very good. They have some commonly observed weaknesses. For example, they have slow sampling speed. People have been using, for example, distillation or one step or few step methods to overcome that. And also it's typically relatively harder to follow specific instructions. For example, if I want to set the value of a certain pixel to, let's say, totally white, it's relatively hard for diffusion models to do that. So relatively a large part of today's workshop, 3 or 4 talks, will be about what is the limitations of diffusion models, how to overcome them, or are some of these existing problems, too fundamental and really needs some other methods or alternatives to solve them. And then to understand what's next in visual generative models, we'll also discuss about the potential of really classic visual generative models in today's context or in 2025 context. So for example, I remember Jun-Yan will talk about GANs, Jiatao will talk about normalizing flows, and Liang Chen will talk about autoregressive models. All of them are very classic generative models that have flourished in some part of the time. Maybe currently autoregressive models have been already flourishing again in visual generative modeling. So our speakers will introduce their experience and practice with all these models, and also will discuss its strengths and weaknesses against diffusion models. And also we'll also discuss some recently newly proposed methods or possibilities for generative models. I think one interesting trend nowadays in maybe last few months is about one-step models, like starting from consistency model and to IM and to mean flow. People are trying to discover or develop one-step models instead of multiple steps that following some inductive bias to be able to do generative modeling or complex generative modeling. So I think everything is possible. Like it seems we're going back, like we're starting from VAE and GAN as a single step generative model, and now we're going back to single step generative model. But in general, all the research communities or all the research happens in this way. Like we always try to propose new challenges and new methods to existing methods. Okay, so here's our invited speakers. I mean, to discuss these topics, we really need a variety of speakers to cover different perspectives. So we invited speakers from, for example, top universities like MIT, Stanford, and CMU. We invited speakers from startups like Black Forest Labs, Luma AI, and Stability AI. And also we invited speakers from industry labs.
Turn it up.
Apple,
Let's go, boys.
Meta, and also Amazon.
All right.
So again, thanks a lot for speakers to join this exciting workshop.
Yeah, voice captions.
So of this workshop schedule, you'll find it in the workshop in the workshop website. So in the morning session, I call it academia session. Well, I don't want to really restrict it to it, but anyway, we will mainly have speakers from academia, from universities, and talking about their insights about generative models from mostly the academia perspective. And also in the afternoon, we will then have speakers mainly from startups and industries to discuss about their insights on generative from the industrial perspective, because I think nowadays this two perspective really matters a lot, and the coalition or the cooperation between these two perspectives is also important. Okay, so that's all for the opening remarks. I don't want to take much time because any 1 minute I saved, I leave more minutes for the questions and answers. So thanks everyone again for joining our workshop, and I wish everyone could learn something new about visual generative models today. Our first speaker is Professor Bill Freeman from MIT, and the title of his talk is After Diffusion Models. So Bill, now is your floor.
It was frustrating. I won't be able to see the other speakers because there won't be any seats available. But anyway, so it's a pleasure to be here. I'm hoping this talk will be somewhat interactive, so if you can keep that in mind as I ask questions. It would be great to hear the answers. I decided to, well, sorry, first, a shameless advertisement. I spent 13 years writing this textbook that I'm trying to draw and so on. And we recently put it online for free, so we had a 6-month blackout period where we then allowed to give it. We had a 6-month period where we weren't allowed to put it online, but now that's passed, and now it's online and it's free. visionbook.uc.edu, and we hope it's valuable to you. Okay.
Yeah, definitely.
Great. Thanks. Why is this there? Okay. So first question, what's wrong with diffusion models? So Tianhong reviewed that a little bit, but I'd love to hear from you all. What do you think is wrong with diffusion models? If you could just call out a few things that you think is wrong with them, that would be helpful. Sorry? Very slow. Okay, what else?
Well, you need to like sometimes one, 2 or 3 different branches of diffusion at the same time. That.
So computationally heavy, if you want to get somewhere, you have to launch several different paths and see if one of them goes where you want to go. Anything else? Hard to control. Okay, great. Here's my list, which is pretty similar. Too slow, not easy to control generation, not easy to edit. And then this bottom one, it bugs me, but I don't know if it bugs anybody else. Not easy to understand why they output any given image. I don't know, I really, I miss understanding things. So then in the spirit of this workshop, let's ask what else might work. What other options are there? So here's just a list, and it's just kind of really more a brainstorming list than a real follow this one by one list. But here's some options: conventional graphics. Okay, let's see how that compares. Hiring an artist full-time to follow around you. Okay, great. Genetic algorithms, simple explainable algorithms, perceptually based heuristics, computer vision by asking nicely. I'll tell you what that means in a little bit. Engineering better diffusion models and something new. Okay, so we'll just go through some of these options, really in the spirit of brainstorming. It seems like the gold standard that we just have to compare generative models with is the thing that is this massive industry that produces all the films that we look at, which is conventional graphics. And so here's what you might say is the weakness of conventional graphics. This is a conventional graphics image made using Blender. And you might say, okay, yeah, it's nice and you have total control over it. Yeah, sure. But look how simple it is. It's really limited in what it can produce. But here's another image made by Blender, and by golly, it's beautiful and has all this richness to it. And you understand every aspect of it. You can go and ask, well, why does that dark spot on the wall look the way it does? And you can go and find out in a straightforward way. And that's really appealing. So then you say, okay, well, why not just do the conventional graphics pipeline? And why not do conventional graphics? Slow. Okay, slow in which, sorry? Okay, it's kind of slow in 2 ways in some sense. It's slow in specifying this rich world because you have to just, I guess the downside of understanding it is you have to be able to specify it. And so that takes a long time. A lot of artists working. And then the other way it's slow sometimes isn't just in rendering it. If you want to do ray tracing and if you want to really capture radiative effects, it might just take a long time. Okay. Let's see, what's easy about it? Mature, fast, efficient pipeline, spectacular quality. Every movie is made this way. There's got to be something to be said for it. And then what's hard, the rendering is complicated, and realistic scenes, rendering of realistic complicated scenes involves a lot of manual work. Okay, the next on the list was hiring an artist full-time to follow around you. And I should say, I used a diffusion model, presumably, to make that image of, responding to the prompt, an artist who follows me everywhere and draws or paints anything I want them to create for me. And that's what you get, the image from that prompt. So I think it's nonetheless kind of useful to look at the pluses and minuses of such a way to generate images. What's good about it is you'd get beautiful, high quality results, creative. Now, it may not have the desired complexity in a relatively short amount of time, just because it takes a lot of time for an artist to generate something. And then what's hard is, it's slow. It might be difficult to say, exactly what you want and how it should be different from what the artist did. So it may take many iterations to get it right. Okay, genetic algorithms. So here's a real contender, I guess. And I should point out that sometimes, where do we look for what's next? Well, often you can look for what happens for what's next. And certainly that happens to the field in the area of neural networks, because neural networks used to be this old technology that was not really being used seriously. And then it was revisited and to great effect. Whitening, kind of standard signal processing procedure, came back later as batch normalization. So sometimes good ideas from the past come back. And there's a beautiful paper from SIGGRAPH 1991, which I have to confess is probably before everyone in the room was born, except me. But I attended SIGGRAPH 1991, and there's this lovely paper by Carl Sims called Artificial Evolution for Computer Graphics. And he kind of led us through how the complexity. You can have these little basic operators like an X operator, the function X, and that gives you the top left image of this mosaic, or you can have the operator Y, which gives you the middle top one, or absolute X, the one on the far right. And he made this little library of Lisp operators that you could apply to images, and then just made a genetic algorithm where you would take two of the operators, combine them in some way, modeling these kind of crossover effects from genetics, and then he would display the result, and then let the user choose the direction of the evolution. And so you start out with these simple operations like the ones shown here, when you can really understand kind of each one of them, and it would very quickly lead you to just beautiful, complicated, artistic designs. And so here's the Lisp function at the bottom right, which generated the beautiful texture shown in the image. And he points out in his paper that if you really think it through carefully, maybe you can kind of understand it, but it gives you just wonderful complexity really quickly. Now you might say, well, that's no different than diffusion models. That's some complicated thing gives you something beautiful. But I should say it's really at a kind of one level higher of modularity than diffusion models or other current generative models, where the base level are just these atomic neural operations that are with literally billions of parameters. And here it's a bit level higher, and you could imagine going and understanding it. And you could imagine also that this would be much more efficient than designing and creating the billions and billions of parameters needed for current models. If you could have something at this kind of one level up of in the direction of symbolism, complicated, yes, but down to the function level rather than down to the sort of atomic level. So this is appealing to me, and I've always kind of thought, okay, genetic algorithms are next. That's what's going to happen. I don't know, but it seems like a good candidate, because you get something procedural. You can have a lot of richness, but it's not quite at the level of neural networks, and so maybe it'll be more efficient in terms of computation. Okay, that's another direction. Now, still another direction might be sort of simple, explainable generative models. So this, in some sense, we go to the past for this. A lot of my past work is on these things of this type. When was this? This is like in 2004. We had a really fun paper we called Infinite Images. Oops, sorry. Where we used, okay, this is just, I guess, to date me, this is using what at the time was a large data set. We had 6 million images from Flickr, and we allowed the user to start at a given image and then apply these operations: forward motion, camera rotation, camera pan. So then here's what we did. Again, it's very simple, explainable, easy to understand. If you were at a given image and you wanted to move the camera to the right, then you would basically move the frame to the right and say, okay, I'm looking for a new image now, which has basically this stuff on the left, what used to be on the right of my former image, and then I don't care what's on the right. And so you go look through your database of 6 million images and find an example, which is kind of like what you had on the left, but something new on the right. And then you want to blend them together. You want to find the best positional match. You want to maybe find the optimum seam between those two images, all very high level, all very easy to understand. And then blend them in the gradient domain, and voila, now you've got this new larger image. And again, it's all very understandable. You started from this picture, you went to that picture. And you could do camera rotations in the same way. You could do zooming in the same way. So here you want to go, you just want to match the center part of the image and find an image that matches that, blend it in. And this gives you, in effect, an infinite playground from your 6 million images. So you can unwrap it and see what you get, and you can show where it all came from, all easy to understand. So the question is going to be, is this sufficient quality? Because it meets the other constraints. It's understandable, it's fast, it's pretty, certainly by today's standards, it's really, really computationally cheap. So let's take a look. Get this out of the way. Okay, so here's how it worked. They're zooming in. And then you have to tell me, is this good enough? Or is this like an early Star Wars movie where it looks kind of okay, you knew what they were trying to do, but it's really not quite high enough quality? Also, I'm sorry to say, it still inherits or has the same, some of the similar control problem issues that diffusion models would have, that you can't really, well, we did make an image taxi. Let me show you that. And then you can explore famous sites and see what's off to the right or left of it. Is it? Oh, yes, sorry. And you can zoom out, zoom out, zoom out, and you can end up at images that you want to end up at. Oh, yes. And then finally, this was, I guess, 2008. You can start from the Windows background screen and see what's off to the right. Okay, fine. So I should point out we've kind of revisited that with recent work that's a highlight paper tomorrow at in the 2 p.m. to 4 p.m. session called Wonder World with first authors Kovin Yu and Hao Yi Duan and senior author Jiajun Wu, who should be in the audience now, I hope. Well, anyway, he's talking after me, but anyway, he'll come. And so this alternative method was, this modern version of it had many similar properties, many similar abilities, but done with, I should say, diffusion models for the, well, Gaussian splatting and diffusion models. So you start with an image and you have a text prompt, and it has multiple layers. It uses a conditional diffusion model to generate a depth map, and puts the images on the depth map with Gaussian splatting. And this is significantly higher quality, significantly higher level of control. I really think it's better in all regards from the older work. So this is a diffusion model, but it's kind of diffusion model plus other things that make it fast, real time, and controllable. Let's back down. Okay, another approach to generating images. I just have to point this out. It's a really beautiful paper on perceptually based heuristics. So there's a lovely, again, SIGGRAPH paper from the mid 2000s of modifying the material properties of objects with purely psychophysics-based, perceptually based heuristics. So they studied what aspects of a surface make it look like it's transparent, what aspects make it look like it's diffuse, and they basically applied those operations to the histograms of various image processing operations applied to these 2D images to create these lovely, 3D looking effects just on the basis of these fast and cheap perceptual heuristics. So what's good about it, it's really fast, it's really understandable. What's a bit weak about it is it really requires manual work, and it's not something you can automate in a very general way, I don't think. I just want to bring that to your attention. Okay, computer vision by asking nicely. This is another way. This is, I don't know, I'm just revealing what's just incredibly frustrating to me about the current academic situation we're in. We have these huge models, and they know about the visual world. They can generate scenes that just absolutely they could not make unless they understood material properties, lighting, 3D shape. But it's hard to get them to tell you what their knowledge of the 3D shape that they just made was, or the lighting conditions of what they just made was. And so you have to coax it out of them. And so I call this approach to vision, I call this computer vision by asking nicely. And you need to persuade the models to reveal to you what the information is that they use to make the image. So here's an example of this. It was in a paper from last year's CVPR called Alchemist. The goal of the paper was to modify the material properties of objects in an image. And again, this was done with a large model. Again, the large model knew what was going on, but we had to coax it out of them. And so to coax it out of them, we had a small training set based on Blender where we said, okay, here's what it means to have a different material property. And we made different examples of objects with different material properties, different amounts of metallicness, different roughness, different albedos, and made a small training set, sort of a fine-tuning set that would let the algorithm know what we meant by having more or less roughness. And then given that fine-tuning, we could go and modify the algorithm to let it, sorry to run through these, but to let it modify the surface properties, which it kind of knew how to do all along, but we just had to coax it out of it. And so here's an example of the algorithm modifying the roughness of a teapot. And then you see this kind of approach in many different papers. And personally, it's amazing what can be done. It's just, I find it very frustrating academically that that's what it's come to. It's saying, come on, please tell me what you know is really in there. And then it sometimes reveals it to you. Any comments about this approach? I mean, I feel like it's pervasive, really, that we're asking these models, what do you really know about what's going on? Okay, so that's another approach. And then still another approach is, well, let's just engineer better diffusion models to try to overcome some of the shortcomings of them. And a lot of that work has been done recently by amazing student that Freya Durand and I shared, Qianwei Yin, in collaboration with amazing researchers at Adobe. And I should say this is another big change in academia, is that we no longer have the computational tools needed to compete at the highest level. It's often the case, and I hate to say it. But so this is a sort of symbiotic academic industrial collaboration that happened, and it's sort of a prototype for things that might happen in the future. This started as an internship project, and then Qianwei came back to us from his short summer internship, and we continued the collaboration with the Adobe researchers, thus continuing to have access to the computational resources of their industrial lab, and they continue to have access to this really strong researcher. And it all works well together, provided everyone works well and we all agree on the direction, which was the case in this collaboration. So this work was designed to address the slowness of diffusion models, And sometimes distilling a large diffusion model down to a single one-step operation is insufficient, has insufficient quality. And so the key observation that the Adobe researchers and Tianwei made in the summer internship was that instead of trying to learn from the teacher an exact outcome point from a given noise sample, let's try to learn a distribution of points. So we want to learn the teacher's distribution of outputs rather than the single best output from a given input noise sample. And that observation, with a lot of engineering hard work, led to just a beautiful, fast, state-of-the-art quality and way ahead of the state-of-the-art in terms of speed, modified diffusion model, which was published at last year's CVPR and also last year's NeurIPS. And the improvements are in the NeurIPS paper. So that's another approach, is to just work harder on these things and make them better. So then here's a summary of these possible directions. Conventional graphics, it's hard to beat, but it's in quality, but it takes a lot of people, it takes a lot of time to compute it. Hiring an artist, well, that's not really going to work. Genetic algorithms, who knows, maybe in the future. They're a little higher level of granularity than network weights, and so therefore it might be a little closer to being comprehensible and therefore controllable. Some of the things from the past that I just couldn't resist showing, they're just too weak, they're not good enough. Simple explainable generative models, perceptually based heuristics. There's the approach of taking large models and coaxing them to do what you want, which is infuriating, but sometimes very powerful. And then just applying more engineering effort on existing diffusion models, I think, is another direction with a lot of way to go still. So I put it in my own mind in this kind of dichotomy that you can have explainable, interpretable, editable, fast, small, clever techniques, but maybe the quality's not there. Or you can have on the right-hand side these super capable, but incomprehensible, slow, beautiful approaches. And it'd be nice to bridge this gap. There's something I just felt compelled to put into this talk. It's kind of asking to predict the future, is to point out that I'm really lousy at predicting the future. So there was a workshop in 2019 where we were asked to say, okay, where's computer vision headed? And pardon any of you who saw this before from 2019, but here was my prediction that, the CNN revolution started from just this, taking the initial first step of human vision and saying, well, let's make a nice, very tasteful engineering version of that and run with it. And it just had huge impact in the computer vision field. And my thought was, and it still is, I have to say, my thought was that, well, let's just do that again. Let's go take the next steps that we think are involved in human perception and go implement those in some tasteful engineering implementation. So those other aspects of human vision, which are not well represented yet, are occluding contour border ownership, contour completion, grouping, divisive contrast normalization, feedback processing. I said, what's next is we're going to put the vision back in vision and learning. Okay, that was my prediction from 2019. And then it turns out, thinking back on it, what happened, it wasn't just an orthogonal direction. It was like just the opposite direction. What really happened that made this big change was to just apply overwhelming scale. That instead of putting vision back into vision and learning, we put language into vision and learning. And that made this huge change. So using transformers instead of CNNs, really ignoring vision in many cases, scaling up model size, scaling up training data, scaling up the training computations, that led to enormous progress. So that's my track record. This is who you're listening to here. But I do have to say, I still believe in that direction that I said in 2019 was where we'd go in 2024. And here's why. all the evolutionary pressures that led to our brains and our vision system, that, that you've got to make a decision really quickly. It's got to be accurate. It's got to be robust. Those all apply to the phones and the vision systems we have in our pocket. You also want to make those. There's a sort of an economic pressure to make the low power, cheap, robust, reliable. So it's all the same pressures that led to our amazing human brains are going to be pushing down on these billion, trillion parameter models that take a Hoover Dam worth of electricity to run. The economic pressures are going to be the same ones as were the evolutionary pressures, which led to the tricks that the human brain uses. And so surely looking at those tricks is going to be a really useful way to go in predicting where economically viable vision and graphics will go in the future. Okay. And then just to, let's see, let me get rid of this. Okay, here's a picture of me and my wife when I was kind of your age, okay? And what did I think at that time? Well, I thought that the plan was we were going to understand how vision works, and then we were going to go out and build a vision machine. And this relates back to the point about understanding. And it's just not the way it went at all. We have vision machines, but we still don't understand how vision works. And it really raises the point in my mind. What does it mean to understand something? Do we need to understand things? I don't understand the telephone directory, yet I use it and I'm happy with that. It doesn't bother me that I don't understand the relationship between someone's phone number and who the person is. Maybe it's just a similar story with vision. Because the current understanding of vision really is, well, there's some Gestalt grouping principles, yada, 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 then 20 billion parameters, and this is an old slide, so I say 1 trillion parameters, and that's how vision works. Didn't we skip a few steps in that description? But on the other hand, maybe vision science is just engineering, and it's not really a science. And I should just point out this list of areas that have the word science in them that are not sciences. So food science, behavioral science, forensic science, political science, actuarial science, those are not really sciences. And maybe vision science is just one of those also, where there's not a simple way to understand it. It's just a set of rules. You follow the rules, you get good vision. And so anyway, just, as someone my age, I find this really frustrating. I want to have a simple story. I want to understand it. And there's one exception to that, one high capacity algorithm, which is understandable. And let me tell you what it is. It's an old one, but it fits my model of what an understandable algorithm is. And that's the Viola-Jones face detector. How many of you know about this algorithm? Okay, yeah, most people, good. So it's just beautiful. It's elegant. It's got beautiful engineering, and it's understandable. So you start out with it uses the so-called boosting algorithm, where you have a sort of cascade of bad algorithms, one after the other, and so it has a nice story then for what it is. What is it that makes a face? Well, a face is something that's got kind of a light, dark part at the top and then bright part below, and that's maybe where the eyes are. And then, okay, it's not just that. You have to also have maybe something that's dark, bright, dark, and that further localizes where a face is. And it's this cascade of that kind of story of successive approximations. So, but it can be in some ways as accurate as you like by just keeping on going with this boosted cascade of simple filters. So that's an appealing algorithm, and current ones are not in that style, I should say. So can we compile foundation models into this kind of understandable story? That's one thing. Can we do it? And the other thing you might ask is, well, do we need to do it? Does it really matter? Maybe it doesn't matter. No, we don't need to compile the telephone book into something that's understandable. Maybe we don't need to compile vision in a similar way. But wrapping up. So another question you might ask, actually, I'd love to hear your thoughts on this. Do you think the next new thing will come from academia or industry? How many people think the next big breakthrough in generative models will come from academia? And how many think it'll come from industry? Okay, 50-50. All right. I think it'll come from academia. I just think that there's all this pressure. There's so much low-hanging fruit ready to be gobbled up from industry that I think there's not a lot of support for someone just sitting in their office working on the next new thing, except in very few labs. But anyway, we'll see. One thing that I do know for sure is it's going to be hard to jump in with the next new thing and have it be as good in quality as the current things are. It's like, there's no way, it's very, very difficult to make something that competes with the internal combustion engine, although I suppose Elon Musk did, but you want to find a path. And I should remind you, when the first, I guess they were GANs, the first really neural network generative models of images, they were so lousy, it was unbelievable. These little 32 by 32 bedroom scenes. And I remember looking at those, okay, wake me up when this is interesting, wake me up when it's ready to be shown. And well, they did. But definitely we're going to have to lower the bar for image quality to allow these fledgling little seedlings of the next new big thing to flourish enough for us to see that, yeah, this is the next new thing, we should go put all our engineering effort behind this thing. So how can we make this happen when we've got all these benchmarks and it's so easy to reject a paper from the top conferences by saying, this is not good enough quality, this is not competitive. So we need something like the Salon de Réfugiés. This is a metaphor that's been put forward by Alyosha Efros and David Forsyth and others. There's some audio that goes with it, but basically, apparently, artists were shut out from having their work shown at the main venues by a sort of cabal of the current leaders in France in the late 1800s, and they rebelled and said, no, we've got to have something that where it's the people's choice. And so they made the Salon de Réfugiés, where it was ones that were rejected from the top conventional art show, and it was extremely popular. People flocked to it. So we need a similar thing like that in our academic world. So I'm just working on title for it. Strong new ideas with weak benchmarks. This is the session that we're planning, maybe. High science, low engineering. Winning ideas that still lose. Anyway, so maybe if you can help me with that, that'll be useful. Great to see you all here, and I'm looking forward to the future talks in this session. Thank you.
I don't understand. I heard he said like the overflow. I think maybe they pull up a Zoom screen there. I don't know.
Okay, we're gonna have one question.
Thank you. I also wonder, like,
Please go ahead. Okay, the question was for the Zoom audience, that I mentioned that these models understand material properties, and we were able to coax that out of them. But he's heard that they don't understand cast shadows. Do I have any comments on that? So I don't know on either way whether that's the case or not. I will point out that there's a lot of papers showing that humans don't understand cast shadows, and it would be interesting and perhaps not completely coincidental if both humans and these large models suffer from the same difficulty. I don't know. Thanks for raising that point. And I guess that's my one question. So let's let Jiajun talk. Thanks.
Okay. Before going into that, I'm not happy. Okay, looks like it works now, finally, great. Well, I feel like there's a great startup idea to actually streamline all these because it takes all this time to set up all these different softwares and have them connect to each other. Okay, so I'm Jiajun, thanks for having me here. I'm an assistant professor at Stanford. I work on, all these 3D, 4D generative modeling with some applications in embodied AI as well. But today, we'll talk about, okay, what's next after diffusion models? And so originally I call this controllable interactive generation of 4D objects and scenes because now you have all these nice, beautiful videos. And of course, you want to go into this world of 4D, or 3D, and then 4D, right? So you want to go into higher dimension where you have much less data, and how can you deal with that? And I think another important aspect of it is you want it to be controllable, right? So you want to really define, because these models are great, but you have some troubles in interfacing them and tell them to do exactly what you want. So is that possible for us to have better controllability? But later, I actually thought about it. I changed this one word, which I actually now like a bit more. Is I said instead of saying it's interactive, controllable interactive, I thought it's also about really it's about intuitive. It's like it provides you kind of an intuition because everything. I think we always choose to use the things that we like and that's supposed to be easy to use and really matches our intuition. And so what would be the interfaces that are so intuitive and feel like, oh yeah, it's just designed for us, right? So in some sense you could argue that why, it used to be like every time I have a question, I go to Google and type some keyword, and I thought this is just the way to go for many, many years. And when GPT came out, I was like, okay, are you sure this is really going to be that useful? And they have all the errors and stuff like that. But now I have problems. I always just go to GPT and just directly communicate with it, saying, please do that and this for me. And what's the answer to this and that? And now it's getting more and more accurate. I almost stopped using Google. So I feel like for generation of objects and scenes, first, we want to tackle hardware problems. The second, we probably really want to think about how to interface with them to have some kind of controllable interface and also very intuitive interface. So that's the things I think I want to do and we're doing. Okay, so yeah, so we can do generation in 2D pixels, but we really want to go beyond that, right? So if you think about the images and I have some similar starting slides, so you may have seen this if you see a different talk, but the contents later are different, and we'll talk about more recent work. But we want to definitely go beyond the just generating 2D pixels. And the reason that we understand, the world is the way it is because even to see 2D pixels for videos, we know there's this underlying 3D or 4D world about object geometry, materials, and all the physical properties that's sort of causally defined and produced, right? It's like here the generator is physics, is the natural world, that they take all these physical properties and produce all the pixels you're seeing here. Right, so in vision, a lot of times we say we do inverse graphics, and we're trying to solve and optimize for these physical properties. So one argument here is if you want to do generation of 3D and 4D, maybe you should think about, again, all these physical attributes, and people are like, okay, if you put physical attributes there, maybe that's kind of constraining because you don't have that much data and it's harder to learn. Yeah, that might be true. But if you think about it from a different perspective, right? And these physical attributes, they also serve as a natural interface that allows you to very easily interact with all these generative models. For example, you can say, I generate this beautiful picture. I often feel like, yeah, something is wrong because I want to, just move the object a little bit to the right. Or I want the lighting condition to be slightly different. Or I want this object, it looks beautiful, but I just wanted to have exactly that piece of cloth or textures on it, right? So when you're thinking about these things, or I'm generating a bedroom, layout of a bedroom with put sofas here and there. I just want the sofa to move a little bit to the right, or I want to have exactly the same two objects but swap their locations. So you're actually, through specifying these physical properties, it provides you a way to interface and control and generate these things you care about. So now the question is, how can we make that happen? Right? How can we use them or control or interact with generative models through these physical properties? So I think we'll say we have explored two ideas. One idea we did it like maybe a few years ago, like 2 or 3 or even longer years ago. And the second idea we're pursuing more recently. So I'm going to talk about both of them. So the first idea we have is it possible for us to have, instead of end-to-end neural network, but having these physical properties in the loop, right? So this is actually pretty similar to a paradigm that was quite popular a few years ago. Actually, now even in some sense is, think about it as you have an intelligent system, but instead of having end-to-end neural network, right? You first have, let's say, like an autoencoder. You have an encoder that encodes raw input into maybe not latent vectors, but underlying physical properties like geometry and textures. And then you can recompose them into render the original scene. So this allows you to learn and discover these physical properties in mostly like a self-supervised way. So example of that is, as for example, like NERF, right? So if you think about NERF, what's going on there is you have a neural network that tries to infer radiance and densities. Okay, and then you go through a differential render. So here you do assume the render has to be differential, right? So you go through a differential render, and there it is like differential version of volume rendering. And that reconstructs the input. But by injecting this inductive biases and the notion that there has to be 3D space, and there's radiance and there's density, and they should interact in a certain way. And here is the volume rendering, you actually was able to discover, pretty good reconstructions of the radiance and density and stuff like that. Right. So in some sense, conceptually, NERF is sort of doing that too. But there's no reason that you have to restrict yourself to just density or radiance. And you can, explore other possible possibilities, and you can even try to reconstruct and recover much richer information. Right. So this is some things we're doing here. And you can train on collection of annotated data, just like in NERF. You can train on a collection of images, but doing testing, right? You can actually go from, actually NERF itself is optimized. If we do things like pixel NERF and stuff like that, right? You can, during testing, you can even go from a single image, and you just take the first half of the neural network, and then it can infer the things to the pair. So some example of that, the work we did, including, for example, in 2023, we explored the idea of how much you can learn just from a single image, right? So if you're here, you see an image of a bouquet of 50 roses, and you may feel like, yeah, they kind of all look kind of similar, but they also look slightly different. It's not like they're identical, but they do look kind of similar. And we understand that we give them the same name, that is, they all called roses. So when I say this is a rose, that is a rose, and this is not a rose, or this is not a rose, there must be something I'm implying, right? So what makes this not a rose, and that is a rose, right? So if you look at the specific instances, and yeah, they're like multiple different instances sampled from same object category, but what makes them share the same semantic category, or what makes them share the same name? And our assumption there is, or our observation there, is really like these objects, they share the same name, or they have the same object category because they share the same underlying distribution of their intrinsics. Right? Think about it. So every object, as I said, has their geometry, textures, and materials. So you can think about it here as, these are just different instances. You have this underlying generative distribution, and you keep sampling from it. Every time you sample from this distribution, you get a specific geometry, texture, and material. And then you can put that together with the rendering process. The rendering process requires what? Requires you put objects in a particular pose and put that in a certain lighting condition, right? So you can keep sampling from it. You can couple that with extrinsics, including pose and lighting. You can render the objects, and here also in the differential rendering way. So think about it as all these Gaussian slats and nerves, whatever. They all sort of different rendering, we can generalize it a little bit, to capture a bit more physical. And back then, because 2003, I should make sure that the real images looks much more like the generated pictures look much like real pictures. So it turns out, right, just by leveraging the assumption that objects have these intrinsics and they can be put into that differential rendering framework, what you can do is you can actually even just learn from a single image and to recover a lot of things. You can actually now trying to generate and sample from it. You can generate roses and see from different viewpoints. You can, as in the bottom row, you can render into different lighting conditions, which is like the second to bottom row. And you can, because you're capturing geometry distribution, you can even sample from it. You can capture different variations of roses. In the middle row, you can see that we can sample and vary the shape and texture of the rose. Right, so you may feel like the results are just like, okay, which I totally agree. But keep in mind that all this is learned from this one single image. There's no pre-trained model even. Everything you just train from scratch is on this one picture. Right? You'll be able to actually do a lot just going from that, learning from one picture. And oh yeah, this is done by I think my PhD student Rinju was great. So there's actually, I feel like if you're putting these intrinsics and putting into rendering framework, you realize that allows you to have a lot of controllability of these generative models. You can change the lighting positions, you can change the pose, you can even sample different instances. Then that makes it very easy to use because you can interact with the generative models and do all these type of changes you want, and maybe generate the roles in a particular case and put that into a game engine and stuff like that. Right? So, and later we had a follow-up where we try to extend it from not only a single object categories, but multiple object categories, trying to discover and capture, leverage what is shared. And here in this case, we're looking to 100 categories of animals, in particular quadrupeds. So there are no snake or fish, so it's all quadrupeds. They have different textures and geometries, and they have some variations there, but they do also share the skeletal structures. They all have similar skeletal structures. So we leverage that, and it allows us to train internet images of 100 categories of animals and to reconstruct them, but also to generate them and to sample them. So you can see we can generate animals of different sizes, different geometries, different textures, and we do capture shared skeletal structure, so that which means you can rig them in almost the same way, right? All these animals can raise their front legs in a certain pattern if you want. Yeah, this is actually this work which was published last year called Learning 3D Fauna of the Web, was led by the PhD student Zhang and my former postdoc Elliot, who has started at Cambridge as assistant professor earlier this year. Okay, so very quickly, this is idea one, because I said this is like something that we did 2 or maybe 3 years ago, so I want to keep it short, and maybe I spend more time on second idea. So, but if you say idea one is great, why do you have to move away from it? So what's the issue here? So here, just like, as I said, you have this kind of rendering in sort of like in the loop, right? You have a simulator in the loop that allows you to interact with these generative models, but requiring a simulator in the loop also comes with a bunch of issues, right? So I think one of the issue is the simulator has to be fully differentiable. And a lot of things that can be made differentiable, but there are also a lot of things that it's hard to maybe be made differentiable. That's why if you look at it, the examples we hear, they mostly look at cases where there's a single object. And the nice thing about diffusion models or all these models are like, yeah, of course, you can actually generate beautiful images or videos with complex backgrounds and lighting effects and stuff like that. Right? And second is, there are all these people doing computer graphics that try to make the simulator differentiable. And it's actually true that even complex lighting effects like ray tracing, they can be made differentiable. If you look at some fancy CVPR papers, they're kind of great. But you also require the system to be very fast because you have to have the training in the loop, right? So you have to every time you're doing like forward, backward. So you require the renderer to be extremely efficient. But that is not very compatible if you want to simulate even differentially these complex lighting effects. So that's why we sort of move on to the second approach, the second idea. And also because the diffusion models are getting better, is if we have already very powerful foundation models and diffusion models, they may know something, they may not know everything, they may not really know how to cast shadows or lightings or whatever. The epipolar constraints may not be fully satisfied. They're probably getting better, but they must know something about it. And at least can we calibrate and evaluate, to what extent we can extract things we care about, the physical properties from these diffusion models in different ways, right? So that's like the idea that we've been moving to. And I'm going to quickly show a few examples. One example is in this year's CVPR, which is oral presentation. So I'm going to talk about here. If you're interested, please go to the oral on Friday afternoon. We want to go from extracting, one part of acoustics is not only geometry, texture, lighting, is also their lifespan, how the object grows and how the flower wilts, right? So it's possible for us to distill. Now the approach is kind of different now. How can we distill from diffusion models to extract object from, like, for example, a video or a time-lapse video of a rose, to extract its geometry, textures, but also to extract how it will evolve over time, so that you can see if you can render in different lighting conditions, see it from different viewpoints, but also capture its growth process, as well as different types of growth process, like baking the bread. And this is done by my PhD student Chen. Oral talk Friday afternoon. And okay. Another example, which I'm going to very quickly show here, is you want to distill from diffusion models, not only about the object geometry, texture, physics, as well as their growth process, but also their physical properties, so that they can react to your perturbations, not just like they grow by themselves, but what happens if I poke this flower, right? So this is actually a joint work done by Coven, who is my PhD student, but also really led by this person, Tianyuan, who is Phil's PhD student. So what happened there is, we want to model the problem of action condition dynamics prediction 3D models, right? You not only want to see it, you not only want to predict, how it will evolve, but you also want to predict what happens if there are certain actions, right? So here, the image, this is actually results. The input is a static 3D scene, which you can get from a few images, and you can nerf it, you can get a Gaussian space out of it. And after that, the output here is an interactive 3D scene, right? You can poke it, you can see, how it will react to different perturbations. And right, so this is kind of some early attempts that we did for. Just be aware of the time. Yeah. Okay. Yeah, some early attempts that we did about how we can actually try to distill from video diffusion models to get object geometry, textures, to capture their growth process, and also to learn about its physical properties. I think due to time constraint, I'm not going to move into more details here. But you're welcome to talk to this person, Tianyuan and Coven, to also know more detail about this work. Okay, Sin, we thought, if here we have diffusion models and they seem to be pretty good and they can give you everything about geometry, textures, or to be honest, it's not really everything. And we notice there are a lot of issues, and we're making some attempts to also trying to think about how we can integrate the two ideas, right? Is that possible for us to more have a kind of a forward backward loop that sort of tie together physical simulation and diffusion models? But just along this line of video generate or distillation, so I think it's also very natural to think about if you can get a lot from these generative visual models, it might be possible to also think about how much you can get from another type of foundation models, which is like those kind of powerful models at the bottom, which is vision language models, right? So vision language models is kind of what started. I call this kind of idea 2A, it's a variant of that, right? Is, the first thing, when people feel like, oh, foundation models are great, maybe image gen or stuff like that was like AlexNet maybe 10 years ago. But more recently, it has been like GPT and things like that. It's stuff from natural language. And what is good about large language models or vision language models is they capture everything, almost everything about semantics, which I can say in more confidence compared with what I can say about geometry and texture, because it is pretty obvious that there's still a lot to do to get perfect geometry and textures out of video diffusion models. But it's more clear that, yeah, we can, all these models seem to be pretty good at understanding the semantics, the meaning of words, the meaning of sentences, and common sense knowledge from language models. So is it possible for us to apply this kind of the idea of distillation to not only learn from video diffusion models, but to also learn from vision language models, so that we can couple the semantics part? Because I haven't talked anything about semantics here, right? So is that possible for us to get semantics out of it as well? So again, led by Coven, in collaboration with Bill and a few others. So in 2024, I think we started kind of a line of work on trying to understand how we can couple vision language models that tells us scenes and semantics, and diffusion models that tells us about the content, appearance, and geometry of the scenes, and how much we can get as much out of it by putting the two together. So here in this framework, which we call Wonder Journey, what we did is we use a large language models to generate a sequence of scene descriptors, right? You can go from a single sentence, you can go from image, but then you ask these language models and vision language models to tell you what is there in the scene, what should be next to it, what will happen if I move around. You have a text-driven point cloud generation systems that try to go from these synthesized scenes to output, gradually you can go from a single image, you can ask what should be next to it, and then you can move around, and you can try to reconstruct the 3D from the original scene, warp it, and then try to in-paint it, leverage, and you can map it, warp it, and map it into the novel viewpoints, and then you can in-paint it using video diffusion models. And you can iteratively doing that. And this allows you to almost construct an infinitely expandable scene. So you can navigate in it, you can go forward, backward, look around. And finally, we also even use the vision language model to verify if the generated scene is good or not. I think that now becomes a pretty popular idea because you can see a lot of the generator verifying idea, and they're both done by these kind of foundation models. Just like 5 years ago, they're both done by GANs, which I think we're going to hear a lot about from Jun-Yan, who is somewhere here already. Yeah, some examples of what we can do is, we can go from a single image and we can generate like an infinitely expandable journey. So in this paper, yeah, we call it wonder journey going from anywhere to everywhere. It's not really anywhere everywhere, but technically you can almost upload any pictures and generate a scene that you can navigate in. And going from a single image, you can generate, of course, leverage the power of multiple generative models. You can generate multiple possible possibilities. And Cohen move on and had this kind of follow-up work called Wonder World. The difference here is now we have a lot more interaction, and I think the interface is also becoming a lot more intuitive, where users can only say, I want to go forward and backward, but user can almost interactivate in close to real time, not really real time, but close to real time to specify we want to see it. So here the user input has, we have user control about moving left and right, but user can also type in language. And here's a demo of what you can do is you can look left and look to the right, but you can type in what you like to see. Let's say I want to go to the left, I want to see an Asian marketplace or an Asian courtyard. But I want to move to the right and I want to see like a future city or cyberpunk style city, right? So you can actually do that in close to real time. And here, the key innovation here is we come up with a new Gaussian circle representation, which is very efficient. And here's some more results from Colin. So conceptually, in a current world, which is actually in a review, we have explored some idea of putting all these together, right? We talk about you have the underlying idea of generating dynamic objects. Also happen if you can distill geometry and texture, you can read objects in different lighting conditions, different poses. If you can distill physical properties, you can predict how the objects will move or interact, respond to your interactions. And you're now able to going from semantic scenes to expand it to generate scenes. But what if we all put this together? Actually, working on that got put in together. So in this most, I think again due to time constraint, I don't have time to go into detail, but we can talk about it offline. But here, demo from any pictures, you want to do action condition prediction in different
Unmute. Oh, okay. You see my screen? Sorry. Very narrow.
It's working, I think.
Do I need to open the video? Like Zoom video? Zoom video?
It's something for the camera. You can open that if you
Oh,
want.
okay, cool. Yeah, great. Thanks. Yeah, okay, great. Okay, so wait, shall I start? Okay, cool. Okay, thanks for coming. I want to talk some our recent work, recent efforts on GAN training. Some of us from our group, but most of wonderful work was from other groups as well. So I want to ask the first question is anyone who have trained GANs in the last 12 months? Or there are a couple of hands, which is great. No, thanks. So yeah, so who are still training GANs? I think there's a joke answer is maybe our lab is still training GANs, but there are a more serious answer is actually there are lots of industry and university are training GANs these days. And the issue, but people don't talk about it. People say, oh, people talk about in the appendix. So we add a accelerate GAN loss and make things slightly better. So they don't talk about it loud, but people are using it. And I would like to try to convince you the GAN training is still needed and why it's difficult, why it might have been made easier. I want to go back to some basics very quickly here. Is the in GAN model you have latent code, you have generated image and a discriminator, try to classify whether it's real or fake image, right? So if you generate a very fake image, discriminator will say it's 0.1, or maybe you have a real cat like my cat, the discriminator will say it's 0.9. And the interesting part here is the generator can take discriminator's feedback, aka gradients, to further improve the score to make it more realistic. And if you replace the latents by the input controls, you can also do like this conditional task. This was a work led by Phillip Isola. Okay. So now the question is, what has driven GAN progress since GAN was invented? I think there are lots of like 10,000 papers, but I think there are lots of loss function papers. They are somewhat useful, but I think the most useful thing is we have better and bigger architectures and led by this NVIDIA group, Taro Kara, etc. So we have StyleGAN 1, 2, 3, and they really make things work much better. I was always thinking if this NVIDIA group decide to work on autoregressive model in 2018, maybe we have a workshop now, what is after autoregressive model. Diffusion model. But anyway, so there are some new ideas. People still working on GANs after 2020. There are some new ideas. So the first idea is it seems like if you train a GAN model on very limited data, so let's say train a GAN model on hundreds of photos, the model will tend to produce pretty bad samples. The reason why it happens, if you train a GAN model for a long period of time, let's say you train a model, the discriminator's accuracy on the holdout test set on the real images will decrease. And this is especially a concern if you have very limited data, like 20% of data, the model will tend to, the discriminator will not be no longer able to classify real images as real for the holdout test images. And if you keep reducing the number of images, this discriminator will tend to overfit to the training set completely. Okay, so one easy fix to prevent overfitting, as we know, is called data augmentation, right? So one easy fix is you can apply augmentation to the real images, to the fake images when you train the discriminator. You can apply the augmentation when you train the generator. Importantly, this augmentation needs to be differentiable because you need to backput the gradients from the discriminator through the augmentation layers back to the generator. So sometimes we call differentiable augmentations. So if you apply augmentation, the model will work much better, especially if you don't have enough images. Okay, so it will reduce FID by 3 times if for the 10% data case, and can make the
the GAN training much better, especially don't have that many images. So this idea of using augmentation is actually quite straightforward. So we actually see like 4 archive paper in the same week. Another paper is from NVIDIA again, called StyleGAN to ADA. So they apply more augmentation, they apply lots of augmentations. So they apply too much augmentation. So in some cases, the training is very difficult. So what they did is they try to make it more adaptive. So they measure how successfully the discriminator can classify real images in the training set. If you cannot classify any images, maybe your task is too difficult, you want to decrease augmentation. If you can classify every single training images as real images, maybe start overfitting, you want to increase augmentation. And there are another 2 papers from Google and from other places who explore roughly the same idea. Okay, but even after we apply augmentation, the discriminator, if you train a discriminator long period of time, you will have a very low validation accuracy, even with augmentation. So the model will still start overfitting. And one thing we can fix it with, maybe we can use the pre-trained model and we only fine-tune the final layer. So if you only fine-tune 1 layer, it's very hard to overfit the training set, right? It's only 1 layer. So now the question is, we have so many pre-trained models. Which pre-trained model should we use, right? So should we use Dino, Clip, VIT, or whatever we use? So one thing we can do is we can try every single model and see which one works. We can always do that, but that's very expensive. Another thing we can do is we can try to have a smarter way to select the models. So one idea here is we can generate some fake samples with the existing generator. We can get some real samples, and we can choose. We can use the pre-trained model for freeze the features, only train the final layer, and see the accuracy on the validation sets. Maybe the VGG model give you 82%. Maybe you have a different model give you like higher percentage, like this Swinty transformer give you 98%, the Clip VIT give you 99%. So in this case, we will choose the VIT model because it's generalized pretty well on the holdout test set, right? And now we add this Clip model to as a second discriminator, and we can keep doing that. We can improve the samples. And now we can do the thing again. We can have this continuous separation test again, and we take the next discrimination, which is the Dino model. Okay. So by using a pre-trained model to help generating tasks, which was actually recently explored by signing, try to align the diffusion representation to the vision models, we can improve the GAN performance dramatically. If you only have 1,000 images, you can reduce the FID by 4 times. You have more images, you can still provide some benefits. Notably, if you are using pre-trained model, you only need less than 1% of the training images to reach the same performance in terms of generation. Okay, so this idea of using pre-trained model again was also explored by other groups. I want to mention this paper called Projective GANs. So in their group, they show they can actually achieve 17 times faster training speed if they use pre-trained model, and this row is the training kind of checkpoints with pre-trained model. This is without pre-trained models, and they also have some new tricks. They add some random projection head to further reduce overfitting of the discriminator. But in reality, none of our papers are completely new. I think there was a very old paper back to 2018. They call perceptual discriminator. So the idea here is we can combine the perceptual loss, which is based on a pre-trained model, by adding some projection heads, and we can train the projection heads, which acts like a GAN. So you have some favor of perceptual loss, you have some favor of adversarial loss. So it's called perceptual discriminator. So it's first explored by this 2018 paper. And since 2023, we were trying to scale up GANs for text-to-image tasks. So the first thing we have tried is we just try to scale up the model. And unfortunately, the model, the FID actually increased. And so we introduced a bunch of things. I don't have time to discuss every single details, but I will talk about 2 things. The first thing is in most of the StyleGAN architecture, they actually don't have any attention layers. So just by adding attention layer to a GAN model, the model will work much better. So here is the StyleGAN model. Here is the latent diffusion model. If you just add some attention layers, the model will work much better, even with the same GAN loss functions. Okay, so here is how it works. We extract some tokens from the clip encoder, and we add some a cross attention layer between the tokens and the image tokens, and we also add some self attention layer within the image tokens. And we also extract the global tokens from the clip, and we have a MLP layer to produce style code. Okay. Yeah. And we also design a multi-scale discriminator. Here is the discriminator will take multiple images at multiple scales, and we also will output real and fake prediction at multiple scales. Again, we add self-attention layer to the discriminator as well. Okay. And this by these efforts, we can actually improve the FID from 30 to 9, and we can use the same architecture for upsampling. The only difference is we replace the constant by a low resolution images. And now compared to the diffusion model and autoregressive model, another GAN paper, style GAN T, we mentioned a minute. Our model actually achieved pretty low FID at a much 20 times faster, because we only requires one inference steps. And here are some samples, and here are some more results. We can actually mix the style, so we can sample 2 text prompts and we feed different style code to different layers, and this can help us to mix the styles. Okay, and the GAN upsampler also outperforms the default stable diffusion upsampler by a large margin. Okay. In short, it can allow fast inference, has very useful latent space interpolation, and also it can be used for upsampling. But we need to be honest about our models, right? So we have a pretty good FID. The model in terms of image quality are still worse than the diffusion model, especially the industry grade diffusion models. So here is the DALI model, and here are our samples. So it's significantly worse than the DALI model at that time. But still, people were spending efforts on GANs. There are papers, there's some recent efforts from other groups. There are style GAN T, which use clip text encoder and dino discriminator. There's a very recent work you try to explore GANs with sparse mixture of experts. And there are very recent paper which open source very simplified GAN baseline which people can use. Okay, this is from Brown University. And now in 2025, the GAN research are moving to a different direction. The directly training GAN is still very difficult, but maybe we can have a very slow diffusion teacher, and it has been trained and has very stable training, and we can distill a very slow diffusion model into a very fast 1-step or 4-step GAN student models. So diffusion model often takes many steps to generate an image. What if we can skip all the steps and just try to have a 1-step model which takes the Gaussian noise and outputs the latents or images directly? There are lots of work trying to distill the diffusion model, like consistent model, flow matching. But in this pipeline, we can actually, a very simple pipeline is we can train a model to directly, train a student model to directly output the image to reconstruct to try to be very similar to the real images, to the generated images from teacher model. So we first generate like 10 million ODE pairs. We have some random Gaussian noise, generate some images or latents using a teacher model, and then we can train a model to mimic the behavior of the teacher models. So the choice of regression loss is very important. So the MSE loss give you quite blurry results, but even you just replace the MSE loss with a perceptual loss, it works actually much better, okay? And it reduces the FID from 110 to 25 and increase clip scores dramatically. But that's the first thing we try. We try to replace MSE with perceptual loss. But one issue with this perceptual loss is, in perceptual loss, you actually, especially work with latent diffusion models, you have to decode a latent to an image, and then you compute a perceptual loss on the image space, right? And this is very expensive because decoding these latent to image take 80 milliseconds in the training time, and compute LPIP's perceptual loss take 40 milliseconds. And it also introduced 15 gigabytes, which means you have to reduce a training batch size, which means the training might be less stable. So we propose a new perceptual loss working in latent space called latent LPIPs. The model will take 2 latents directly and output whether these 2 latents are similar to each other or they don't look like each other. And this avoids the decoding step, and it reduces the training speed by 10 times. And also, more importantly, it reduces the memory. So we can we can add a discriminator later, we can have a large batch size. Okay, and then we can add a conditional GAN loss on top of this latent LPIPS loss. So we generate images, we compare to the ground truth teacher outputs, but we also add a discriminator to classify whether this is a real latent or this is a fake latent. We're using a conditional discriminator, so that the model conditioned on the Gaussian noise as well as the latents. And we initialize this discriminator using pre-trained stable diffusion models. And again, the discriminator take latents at multi-scale and outputs whether it's real or fake at multi-scales. Okay, and here are comparison. This is our results compared to the teacher model, compared to the GAN training from scratch, and compared to the instance flow. Here, the comparison between our model and latent consistent model as well as the flow-based models. So you can see actually, if you just train a GAN model, conditional GAN like a pix2pix, it's actually very compatible, very comparative with respect to all the consistent model and the flow matching method. So the GAN distillation is actually kind of a clouded area. I would like to say there are lots of recent work and concurrent work. Any kind of SD turbo was using the third loss. There are UFGN, SDX lightning from ByteDance. But the nice thing about the GAN distillation is you can actually combine the GAN loss with other loss. Like if you like regression loss, you can add a perceptual loss. If you like score distillation loss, you can combine the score distillation loss with the GAN loss. You can also initialize your network with some kind of progressive distillation, consistent distillation, and then you further add a GAN loss. So it's very flexible. There are more recently, there are lots of efforts who are trying to train a one-step video model from ByteDance. I want to show some work from their group. They can generate this is a 2-second video, but they have a recent version. We can generate a 1-minute video with GAN-based autoregressive models. So there are some design choices. I try to explore. There are different authors have different opinions. So whether you want to add a discriminator in the pixel space or latent space, or whether you would like to have a conditional discriminator which take both the Gaussian noise and latents, or you just take an unconditional discriminator which just take a latent as input. So the nice thing about conditional discriminator is you can leverage the ODE pairs. The nice thing about unconditional discriminator is you can just use real images. You can just feed real images to the discriminator, and it might have a chance to outperform the feature model. And there are also other debates whether the discriminator should take a clean images or should take a noisy images, because the discriminator initialized with diffusion models, it works better with noisy images. But on the other hand, if you add noise to the image, since we are not doing the denoising anymore, we just try to classify it with real and fake. Adding noise sounds like not a good thing to do. Okay. There are also some other design choice. How much tuning we need for the discriminator? Are we just tuning the projection head? Or we try to fine-tune the entire network. We try to have a low fine-tuning to reduce the training memory. Okay, I will leave these details. Happy to talk about after talk. But I want to have a discussion on why are GANs hard to train? So I think I heard about these answers. The GAN is very unstable. There are some multi-class. That's true, but that doesn't help us to make training better. Like you can say, the training is not stable. So what should we do? But there are very more kind of details to what's making it very hard to train. Is actually when you train a diffusion model, you only need to figure out what's the best architecture for the generator, right? The DIT or UNet, or how many blocks, how many layers. But when you train a GANs, it requires architecture search over 2 models. So each model have n choice, each model have 20 choice. You need to train 400 models. One autoregressive model, diffusion model, each model have 20 choice, and you need to train 20 models. And this was not an issue in the style GAN time, because the style GAN training costs maybe $10,000. But if now the training costs $500,000, you don't want to train 400 $500,000 models. So it's very hard to search for the best generator and discriminator for GANs. And also, I would like to argue the single-step model is very hard to train. It's just nobody can train a single-step diffusion model from scratch, or nobody have trained a single-step autoregressive model from scratch. So the multi-step model is just easier to train than a single-step model. But if you want to train a single-step model, your only choice is GAN loss, because the GAN loss works much better than the regression loss or castration loss for a single step. So in conclusion, I think multi-step is just easier to train than single step, but somehow the diffusion model and regression laws and classification laws can train multi-step models, and your only choice for single step model is GAN laws. So people feel like the GAN is harder to train than diffusion model, but in reality, the single step model is much harder to train than multi-step models. And there are also lack of open source efforts of style GAN series, which make things a little bit hard to reproduce and develop. Okay, and there are more answers on that. Like for example, another things which people don't notice that is actually GANs are more compatible with ConvNet and less compatible with attention layers. Since the attention is replacing ConvNet, so the GAN is also not that compatible anymore. The reason for that is self-attention layer is not Lipschitz for any LP norm, which is a very critical thing for the discriminator training because you want the discriminator to produce very similar score for the similar inputs. Oftentimes, when we train again with attention layer, we have to use L2 attention layer, which has have a constant Lipschitz by itself, but we don't know whether L2 attention layer works better than the original attention layer or not. And also the GAN training is actually very memory intensive in some sense because you need to load two models, you need to load generation discriminator. So as a result, you have to reduce the batch size by half, which makes training unstable. And sometimes you have to use something called R1 regularization, which is to compute the gradients on the discriminator and try to compute the gradients on this gradient, try to make this gradient small so the discriminator will behave more kind of smoothly. And this regularization layer requires higher order gradient computation, which is not compatible with lots of things like flash attention, not compatible with multi-node training. So, and it could increase memory, training memory by a lot. So there are some solutions. For example, you can apply this regularization every 10 iteration. You only apply regularization on a small number of images in your mini batch, or there are some approximation which try to avoid computing these higher order gradients. Okay. And there are another things which, according to Xun Huang at Adobe, he told me that most of the optimizer, Adam, whatever optimizer is designed for a fixed objective function. So that's why with the moment makes sense, right? Because you are optimizing the same thing, so you want to track the history. But again, is a moving objective function, so the solver is actually not working that well for that. But I also want to share some good news. Is actually the conditional GANs are much easier to train. And most of the time we use GANs for conditional tasks for like image tokenizer. We go from latent to images, upsampling, we go from low resolution images to high resolution images. In kind of controllable tasks, we go from sketch to photos. So most of the time we are actually training conditional model. Even for distillation, we are distilling from the Gaussian noise and images, and we have ground truth pairs. So it's conditional training. It's much easier to train. And for example, recently we have trained a model on a one-step, we call Pix-to-Pix turbo model, which you can, it's actually very comparable with ControlNet, but with 50 times faster. So here is you have a cat and you can draw a cat with a one-step model, and it only requires 0.1 seconds in a 100 GPUs. And you can type text prompt as well. You can say, I want a black cat, I want a white cat, or maybe you're not a cat person, I want a dog, and maybe a husky. So it's achieved by a single step GAN model. Okay. So another good news is GAN models actually made training made easier. So we can use lots of pre-trained model as a discriminators, or we can use a pre-trained diffusion model as discriminator as generator. And since for distillation tasks, we don't need to do architect search anymore because we just initialize our generation discriminator with the pre-trained diffusion model, so you don't need to worry about architecture search. Okay. Training, though now why are we still need training GANs is most of tokenizer were trained with GAN laws. We can distill a slow model into a fast GAN model. You can also perform conditional generation tasks. You can do upsampling with GANs. And another interesting thing I noticed that is actually it's very hard to do unpaired learning with diffusion model because you always need to have a reconstruction loss. Most of the work with unpaired learning was still done by GAN. Even I think everyone is using ControlNet and Pix-to-Pix, but I was still trying to, there are still people ask questions, oh, how do we do cycle GAN for this task? I was like, why don't you switch to diffusion model? Okay, so I still have 1 or 2 minutes. I want to show some other works we in our group was doing, which, so one thing we have been working on is we try to build framework to allow model to generate real objects, like a painting rather than digital assets. So here we have a robots and human co-painting system, which robots can create a painting with the help of generative models. We have another work, we're trying to build a real world Lego model. So here we try to output a sequence of instruction, and we can create a very relatively small scale Lego designs with the generative models. And this involves, we need to make sure that the structures are physically stable. So we have some physics model, and we need to make sure that you can actually build a structure. It's not just an asset. Okay. And so to show that, we actually, you can build it by robots, but also you can manually build it. You don't have to have robots build it. We build lots of Legos by ourselves. Okay. Another thing we have been working on is we're trying to improve the 3D generation with kind of tactile sensing, like geosite sensors. So if you do a text 3D, the texture is always very flat. But if you can actually capture a texture using a geosite sensor or tactile sensor, you can make the texture of the text 3D outputs much more realistic. Okay, I would like to thank my collaborators and students. I think Mingu and Nupur did most of the work. They are the leading team of students also. And thanks for your attention.
Yeah, so still because of tight schedule, thanks Jun-Yan again. And the next speaker. You can also share your screen.
Good.
Yes.
Okay, testing. People can hear me on Zoom. Okay, so let me know if I need to change anything.
Yes.
I'll move some of the clutter. Yeah, thank you.
You can hide it with more.
Great.
Force one.
Okay. Cool. So I think we're all set. So yeah, thank you for hosting this workshop and inviting me. I'll talk about language as a visual format. So I think I have to start this talk by saying how much I love pixels, because I'm going to talk about language instead as a different approach. And I really like this quote. I think that I attribute it to Jitendra Malik. It's, I think, been passed around the field, but the advice is that in this field of computer vision, we should, strive to become friends with every pixel. Like really look at the pixels. The pixels are where it all starts. It's in the data. You have to understand the optics and the color spaces. And I've done that a long time in my career. We wrote this textbook with Bill and Antonio, and the cover is about pixels. Like that's why it has those funny colors. We were thinking about pixels. That was the design. And the dedication to the book is it's dedicated to all the pixels. Okay, so I just love pixels. If you see Antonio, I saw him earlier. I think he actually might be wearing this shirt. You often see him wearing this wonderful shirt, the pixels, like Abbey Road style. Okay, so I love pixels. The people I've learned from love pixels. They're great. But maybe they've led us astray. Okay, that's going to be what this talk is about. And what's after diffusion models? Well, diffusion models are all about diffusing pixels right now, maybe diffusing some latents, but what if we switch our representation entirely? Okay, so the tyranny of the pixel. I think, we live in a world that is, it's the pixels world. Convolutional networks, architectures that we've developed over the years, they all start with these grids. They're all based on these square lattices, right? And we think about padding and all these little details. It's all about this fundamental choice. We started with little square visual elements as our first part of the processing. And you might think, well, now we have transformers, but it's patches. It's almost the same thing. Like, why did we do this patch thing and break the image up into these, square patches? Well, it's derived from the pixel somehow, in the pixel way of thinking. Yeah.
Well, the Zoom slide is out of sync.
The Zoom slides are out of sync.
Yeah.
Anyone
Do you know
why?
No, it's not variation.
Okay.
Do you share the correct?
Okay, maybe I'll just try resharing. I'll just share my desktop. Okay, did that work?
Can you change?
Okay, there's a slight lag on the Zoom, but I think it's working now. Okay, so yeah, we live in the pixels world. We live in the patches world, which are kind of derived from pixels, bigger pixels, groups of pixels. And this has informed so much of our field. Like, why do we do this weird thing that Kaiming might, or Kaiming has done? It's just a strange thing to do. Sorry. And even like you go to RL and robotics and you think we're going to get away from pixels over there, but no, we're still living with pixels. It's like Minecraft is the benchmark and it's voxels, but they're just big pixels. So we live in this world of pixels, and I think that really has been powerful but constraining in some ways. So let me give you, I need to hide the controls. Let me give you a brief history of visual formats. So we had about 20,000 years of paints and graphite and sculptures and pieces of rock stuck together. Okay, so 20,000 years ago to 1957, that's our visual format, but we didn't have pixels. And you might not know it, but the pixel had to be invented. And there's a guy, Russell Kirsch, who invented the pixel, or he's considered the one who invented the pixel. He did scans of photos and started doing the scan, breaking it up into these discrete elements that he called pixels. And so here's one of the first images made out of pixels. And then in our modern era, we've had a lot of other ideas, representations based on lines, representations based on implicit level sets and radiance fields and other types of things. And now we have a lot of embeddings. We might not work directly with pixels, but with features. But still, the pixel is the starting point. It's the dominant thing. Okay, so what if we just say all that visual representation, it was all a little bit off, and actually language could be a different type of visual representation. And so the way to think about this is to go to stories like Proust's description of the Madeleine dipped in tea. And you can, of course, visualize that in pixels, like shown here. But here's the excerpt from Proust. He said that she sent out for one of those short, plump little cakes called Petites Madeleines, which look as though they've been molded in a fluted scallop of a pilgrim's shell, and a dole day, a soaked morsel of the cake. These are all very evocative sensory descriptions. So why is it that we consider the top thing, the image made out of pixels, to be visual, and the bottom thing to be not visual, to be language? It is visual. It's visual language. It describes photometric properties of the world. It describes colors and shapes and so forth. Okay, so that's the theme of this talk. What if we switch our entire way of thinking about things to our basic units of representation will be text instead of pixels? Okay, it's not that crazy an idea because, of course, we're all using LLMs and VLMs and so forth. But I want to think of it a little bit more dramatically than that, not just like using NLP methods to integrate them with vision models, but just saying, why don't we just work on text as our format? Why isn't that the visual format? Okay, so just some thoughts. So I'm going to talk about two different projects. First, I'll talk about some work that we've been doing on comparing how similar or different are the representations in language models of the visual world to representations in vision models of the visual world. So does a vision model see the world in the same way as a language model sees the equivalent language description of a scene? Okay, so if a vision model looks at an apple, it creates some embedding vector. How similar is that embedding vector to the embedding that you would get if you process the word apple in an LLM. So is the word-to-vec representation of apple the same as in some sense, the same as the like VIT image embedding of an apple, of a picture of an apple? Okay, and the way that we've been looking at this, it comes from this field of representational alignment. One of the ways of characterizing representations is by what are called their kernels. So the kernel is going to be the way that the representation measures similarity between different data points. Okay, so we'll restrict our attention to vector embeddings, so mappings from data to embedding. That could be a visual embedding or a language embedding. We're going to characterize the representation by the kernel. An example of a kernel is shown on the left here. And the kernel is just this pairwise function that takes the embedding of data point xi and measures the distance or the similarity to the embedding of data point xj for I and j varying. Okay, so the kernel for a vision model might look like this, run over emojis. The apple is considered similar in embedding space. Like if I take the dot product between the apple embedding and the orange embedding, those are considered similar. And the apple and the elephant are considered different. And the way that a representation measures distances is captured by this matrix. And that's a fundamental object that informs most of the kind of theory of how this representation will generalize, how it will function if I use it for nearest neighbors, for example, because that's all just based on distances. So how a representation measures distances is a fundamental way of characterizing it. So what we've been looking at is how similar or different are the ways that vision models measure distance to the way that language models represent distance. So it's the similarity of similarities. So we can look at the kernel for Dino evaluated over images and compare it to the kernel of Llama or some language model evaluated over the captions of those images. So does the way that Dino represents a picture of an apple does it have the same distance structures as the way that Llama measures the caption apple or the word apple? Okay, so I'll just show you the main, I think the most interesting result from that line of work, which is that we can measure the alignment similarity between the kernel of a vision model and a language model on the y-axis. That's alignment to Dino in this case. And on the x-axis, we're going to plot the performance of the different language models that we evaluated this on. So the performance of the language model at doing next word prediction. And the interesting thing is that as language models get better at next word prediction, their alignment in terms of their kernel structure to Dino increases. And as the Dino model is made bigger, its alignment to language models also increases. So it's like, this is a quote from another book, Everything That Rises Must Converge, this idea that as systems become optimized to fit the world and do better and better, like somehow there's a convergent force there. I'm not going to go into all the details. We have a position paper on this. We call it the Platonic representation hypothesis. So there's a lot more arguments in that paper, but this is the main empirical finding that we had. Okay. So there is some degree of similarity between how language models represent language descriptions of the visual world and how vision models represent pixel descriptions of the visual world. But one of the really interesting and important points is that, well, language might be much more impoverished. It's very short. These captions, like an apple, it doesn't describe the color of the apple, the whole experience of the apple, but the pixels have a lot more information. So in order for language to truly be aligned and have the same capacity as vision to represent the visual world, as pixels to represent the visual world, we might need 1,000 words, right? An image is worth 1,000 words. And we actually found evidence for that in that work, which is this experiment where we measured the alignment to Dino on the y-axis again, and on the x-axis we measured the length of the caption. So we can take detailed captions or short captions, and as the captions become more detailed, of course they have more information, they describe more, and they end up representing the world in a more similar way to how the vision model represents the world. So it kind of makes sense. If I have a whole paragraph or a book, I can really tell you everything about the colors and the shapes in an image, or that's a hypothesis. I think that's probably true with enough text, you could represent all the visual detail. Okay, so that's led us to the next project, which is, well, could we make it so that captions, so that language descriptions are more visually descriptive? Can we actually improve the alignment between vision and language? Okay, how are we doing on time, by the way?
It's 11.
Okay,
that's
15 minutes. Perfect. Okay, good. Thanks. Okay, so here is a system that we're going to try to improve. This is going to take an image and produce a caption, but there's a problem. Image captioning systems right now are mostly trained on captions that humans write, and humans might not write a very interesting caption. They might write a short caption or a meme, or, you know, right? They're not trying to create an accurate, faithful language description of the visual world. And this would be a much better caption. So how do we prefer this caption, which talks about all the different details of this image, and prefer that caption over this caption, which is too short? Okay, so we're going to use the following idea. We're going to notice that this short caption has the problem that if I tried to reconstruct the image from the caption, it would not know what the color of the background is. It would not know what the color of the paint is on the cup. It wouldn't know what the latte art looks like. So what would it do? It would maybe hallucinate. It would just make something up. It would make a guess. So this is a reconstruction through a text-to-image model of the input that was processed through an image-to-text model. So it goes image to text back to image. And now we can do what, you know, Jun-Yan was talking about, what we've also thought about in the past, which is we can measure the cycle consistency. So we can look at the dissimilarity between the input and the output and say, therefore, it lost information through that cycle. This bottleneck of text lost information. But if we had this long text, we can do the same experiment, and now here's the output. And you might be thinking, I mean, to me, this was actually quite surprising to see results like this, because it's like, wow, how did it know, you know, the exact shade of blue? That caption doesn't say it. It says, I think it says blue somewhere, or maybe not, but yeah, blue floral patterns. But why that exact shade? Well, because it's bias, right? It's our world has bias. That's a shade of paint that's used in these cups very often. Okay, so there's photographer bias, there's structure to the world. So you don't need a lot of text when you can combine it with like strong priors from generative models. And those are much more similar. Okay, so we're going to use this idea of cycle consistency to create a image text alignment reward. And this is work that we put out recently. It's on arXiv called Cycle Consistency as Reward, and it's learning image text alignment without human preferences. This is work that was co-led by Hyojin Park and Caroline Chan. Okay, so data, code, website, it's all available for you to check out now. Okay, so here's the basic idea. We have the space of text, the space of images, and we could train a mapping from text to image. We want to know how good is that output image for that text, and we'll check that by trying to map back to the text space to try to caption that image and make sure that the reconstructed caption actually describes everything that was in the original caption. So it shouldn't hallucinate, because otherwise there would be new details in the caption that weren't in the original caption. And it shouldn't miss information. If it didn't tell me what the color is and the layout is, then I would not have a faithful reconstruction. Okay, and we can do that in the other direction too, of course. So we could map from an image to text, and then check how good that caption is as a description for the image by mapping back to the space of images and measure image similarity in the space of images. Okay. So this is actually an idea that's been explored quite a bit in the last few years. I'll highlight one paper from our wonderful host here, Tian Hong. So Tian Hong and his co-authors had this paper where they were learning representations using cycle consistency between text and images. Another example of this kind of work was in DALL-E 3. So DALL-E 3 had this interesting idea that a popular idea in a lot of generative models now, but I think it was at least novel at that time, to my knowledge, which is I will use an image captioning model to create synthetic captions for images, and then use that as training data to train a text-to-image model. So it's implicitly creating data that forms these cycles. So that the cycle idea is in that paper too. There's a bunch of other papers that have talked about using cycle consistency as a way of improving image text alignment. Okay, so our paper is exploring that. We think it's a good idea. We're exploring that in more detail, but our kind of specific contribution is a reward model that checks for cycle consistency. So a lot of these other methods, they ran the text-to-image model, and then they checked image-to-text model, checked cycle consistency. It's a slow process. It might not be differentiable. It might not be used as like a reward function that can be optimized. So we're trying to make a lightweight, fast, differentiable function that just takes text and image as input and outputs a score. Okay, so think of this like a drop-in replacement for clip. It has the same protocol as clip. Image and text go in, one pass through a model, scalar score goes out, and you can optimize against that or use that for selecting, for guiding your system. Okay, and then we have experiments that show that this seems to actually improve things. So that's a spoiler. Okay. Okay, so how do we do this? The way we do it is we set it up as a preference modeling framework, which is very popular in language modeling right now. So what we do is we take an image, we generate several different captions for that image using different VLMs and potentially different random seeds. So there's some randomness and we can get different captions. Some are better than others, right? So this has 2 captions. And what we'll do is we'll check the ability to reconstruct through the image, the text-to-image model, the original image. And one of the captions reconstructs an image which is quite similar in feature space, and the other caption reconstructs an image which is quite far away. And we simply say that the low similarity reconstruction will reject that caption. We'll call that like a negative sample, and we'll call the better reconstruction, the caption that led to the better reconstruction, a preferred sample. So we have positives and negatives. Okay, so here's some examples. We take our cup, we caption it, 2 captions. The short caption leads to a bad reconstruction. The longer caption leads to a better reconstruction. So we say we prefer the top caption over the bottom caption. Here we do it the other way. The input text, we have 2 generated images. I'm not gonna, you can read through it maybe after the fact. I'll put these online. But the reconstructed text is better in the top case. It's more accurate. When in the bottom case, I'm highlighting in red hallucinations. So that water tower, that white sphere, is not mentioned in the input caption. So it's like a hallucination in the generated image, and we can identify that there should be penalized by saying that the reconstructed text has words, nouns that don't exist in the input text. Okay, so we create a big data set of these triplets, input, image, and 2 possible text captions, and which one is preferred.
Just left.
Or
I think
input text and 2
yeah, it's
possible
occupied.
image reconstruction, and 2 possible image generations, and which one is preferred. And there's a lot of these kind of preference data sets for reward modeling. And the big distinction between this one that we have and the prior ones in this field is that the prior ones were all, or to my knowledge, they were all collected with human preferences. So you ask humans, which caption do you prefer? Or you ask an AI, which caption does this AI prefer? Which caption does GPT-4 prefer, for example? Okay, but this one doesn't involve humans or AIs. So it's like self-supervised, it's automatic. Just checking for a structural property of the mapping. Okay, so then you can train your reward model on this preference data. So you have triplets, image, 2 captions, which is preferred. You train a model that will try to score highly the preferred caption and score lowly the non-preferred caption using what this thing called a Bradley-Carey loss. Okay, so you can train this in either the text to image to text direction or the image to text to image direction. So just walking a little bit through this math here. We have our reward model that's parameterized by theta. We're optimizing to learn the parameters theta, and we will try to increase the score that we put on the input text and the preferred caption. So we'd have high score when there's good alignment according to cycle consistency, and low score when there's poor alignment. And we can do that for preferred text versus rejected text, and so that's kind of the other direction, and we can combine them. So we're looking at the cycle from image to text to image, or from text to image to text, and we can just average them together. Okay. So what can you do with this reward function? You can use it for 2 things. It can be a metric for assessing if you have good alignment between text and images, or it can be a reward function that you can optimize against. So you can train a model to optimize, or you can do a test time optimization as well to try to find the caption that is the best fit for this particular image. Okay, so let's first look at assessing image text alignment. So the way that we look at this is we have a data set of input image and 2 captions, and we have ground truth. So what does ground truth mean? Ground truth just means what the data set creators for these benchmarks that try to evaluate captioning have decided is the correct caption. So some human that has decided that is the correct caption. And we can look at how a lot of different methods that are, like CLIP is the most popular one, but there's a bunch of other methods that score image text alignment, and they all decide on which one they prefer. So there's a lot of details here. We can look at this in the other direction too. We can go from input text to 2 possible images. There's a ground truth of what the data set creators said is the correct output, the preferred output according to humans or designers. And you can see how different models agree or disagree with the ground truth. Okay, so the ground truth is always the left of the 2 options. Okay, so we ran those experiments, and on these benchmarks, especially on benchmarks that care about detailed captioning, so there's certain benchmarks where humans have decided which detailed caption is the more accurate caption. And on those benchmarks, cycle consistency really increases the agreement with the ground truth. So it helps us to create more, it correctly scores that a correctly detailed caption is better than an incorrect detailed caption. So we have state-of-the-art performance on evaluating detailed captioning. For text-to-image generation, we have performance that's comparable to the existing reward functions that are derived from human preferences, but the interesting thing is there's no humans involved here. So we have agreement with human preferences, like there's methods like image reward and pick score that are based on human preferences. And also interestingly, the reward model is somehow outperforming if you just did raw cycle consistency where you didn't train a reward model. So there's some kind of distillation of going on here, regularization. Okay, so the other thing you can do is improve image to text alignment. Okay, just doing time check. Okay, good, a few minutes. So in this case, what we'll do is we'll just try to find the caption that maximizes our reward. There's a few ways you can do this. One of them is test time optimization, where I'll just for simplicity use best of n search. So best of n means we will run our captioning model n times with a different random seed each time, and we will use our reward to predict which of the outputs is the best, and we'll see if that actually improves the quality as assessed by benchmarks or humans. Okay, so here is our initial caption. If we just run a captioning model once on this image here, and you can see it will hallucinate a few different things. This is the building is covered in moss. That's not really reflected visually. If I zoom in, there's no obvious moss. And there's a looming mountain in the background. So we have hallucinations, right? That's a big problem. If I run my captioning model 250 times and I use cycle reward, our reward model, to pick the best of those 250 times, it does two things. One is it actually makes a longer caption because it prefers long captions, detailed captions. And two is it got rid of those two hallucinations. And again, you're gonna have to trust me because it takes too long to read all of these, but those two hallucinations are gone. Okay. So quantitatively, you can see on these benchmarks, as you do best of n search over more samples, according to our reward model, you will improve performance on certain benchmarks for detailed captioning. So the blue lines are our methods, and the other lines are comparisons like VQA score and clip score and a few other ones. You can do it in the other direction too. We can take a caption, we can generate an image, we can then try doing that 250 times, choose the best according to our learned reward model, which we call cycle reward. And initially it kind of messed up some of the, the adjective noun alignment. So it decided that rather than a floating sphere, there's a floating cube. But that was corrected once you have 250 tries and you pick the best one that's most cycle consistent with the text. Okay, in that direction, we get the same result again, except an interesting thing here is that VQA score actually does better than us on this direction. So one finding from this paper is VQA score is actually a great image text alignment for image generation. Okay, for graphics tasks. Okay, so you can also do this not with best of n, but with DPO or potentially RLHF. We only tried DPO in this so far. You take an image, you fine-tune the model in order to prefer the caption that cycle consistency prefers. And so again, the same thing happens. You get more detailed, more accurate captions by doing this. You can do it the other way as well. So we use DPO to optimize an image generation model. And now this museum description that has priceless works of art on the walls, well, it added the art because it needs to add the art so that you can reconstruct that text. Okay, the original model forgot to put the paintings in the image. Okay, so yeah, there's a pip install for this. Think of it kind of like Flip. So if you have something that uses Clip or image reward or VQA score, you can just pop this one in there. Fast, differentiable, and yeah, hope you try it out. So let me conclude by saying that I've been interested for a long time in how different ways of viewing the world are all somehow alike, how you can translate between edge maps and photos, for example, in this old work, Pix to Pix. And recently we've had this idea that, well, this happens because fundamentally there is a world out there, that's the idea. And all of these different ways of depicting the world, edge maps or photos, or maybe even text, are just different projections of that underlying world. And so all these different formats that we have, audio, text, images, edges, whatever, they're all just superficial views, right? The shadows on the cave wall. And I don't know, that idea just is stuck in my head and I can't get away with it from it. And I think that it's interesting to try to apply that to text and think of text as, or language as really a first-class citizen for depicting visual information, an alternative to pixels, an alternative to line drawings. And the only thing is it requires visually descriptive text because an image is worth 1,000 words. And so that's where this idea of cycle consistency comes in, where we can try to make more visually descriptive text to make it more of an equivalent citizen to pixels. And so that's my rough idea of what's after diffusion is let's just move to language and just generate language as our data. Not even try to make pixels at all. Like the end result is just Proust descriptions of the visual world. But I still love pixels. So what's after diffusion? Like the pixels will come back. We'll come back and we'll do cool things with them later. Okay, I'll end there and thank you for listening.
Yeah. Okay. So the next speaker, let me thank Phillip again. So the next speaker.
Yeah, unmute yourself and also share your screen on them too. Yeah.
What does it mean? Continue to share.
Like which Wi-Fi are you joining?
I think it's
Oh, it's not.
okay.
Can you like click a little bit like on the to make sure the site is working? So
Well, it looks like this is not working. It doesn't connect to this one. Anyway. Oh no, it's the focus is working. Is it working?
yes.
Okay, good. Cool. Welcome everyone. I'm going to give the same talk the third time. If you happen to listen to that, then I apologize for the duplication. But yeah, today I will talk about some work of my research team on training some end-to-end generative models. But before we talk about generative models, well, let's talk about recognition. For example, classification models. Actually, since the introduction of AlexNet in 2012, people have get used to end-to-end recognition models or classification models. Given an image and we want to classify it by some class labels, or we want to map it to some semantic attributes such as bounding boxes or segmentation masks. What we will do is that we will process the image by one layer, another layer, and so on and so forth until it reaches the outcome we have. And then we will have an inference time computational graph, which is what we will do when we do the inference. And then we will conceptually, we will just reverse all the operations here. And then we will train the model by this reverse, which is known as backpropagation. Well, this is basically what we are doing every day. But actually, this is not the common practice before AlexNet was introduced. So actually, before that, before 2012, layer-wise training or layer-wise pre-training is actually a more popular solution. So here I list two options for layer-wise training at that time. So one is known as deep leaf network. The other is known as the denoising autoencoder. So basically, the concept here is that if you want to train a network that has many layers, you don't train them all at once. Instead, you train them one by one. For example, you train the first layer using some unsupervised objective, or what is referred to as self-supervised learning objective today. And then you freeze it, and then you train the next layer, and then you freeze it, and you train the next one, and so on and so forth. So as I said, for every single layer, you need to define some objective, and usually this objective has nothing to do with the labels. It is unsupervised. Let's take the denoising autoencoder as one very simple example.
let's say if you have some representations from or some features from your previous layer, you freeze it, and then you add some noise to it, and then you train yet another autoencoder, encoding, decoding, and then you do the reconstruction. And then this is how you can obtain the weight for your second layer. And then you retain the encoder and you train the next one and so on and so forth. So this is actually how people used to train neural networks before AlexNet, before what we get used to. Okay, now let's come back to generative models. So actually, in some sense, today's most powerful, most popular generative models, such as diffusion models or autoregressive models, are kind of layer-wise training or layer-wise pre-training in this regard. So for example, in the case of diffusion models, you start from, at inference time, you start from a noise image or a noise map, and then you applied one step, let's say, which would be an entire neural network, but then it will turn the input into a less noisy map, and then you do it again, and then you arrive at an hopefully good image. And then actually what you are doing, what your computational graph is at inference time is this bunch of steps. And every single step here is one neural network. And similarly for autoregressive models, you start from an empty sequence, and then in the first step, you use an entire neural network to predict one token, and then so on and so forth until you arrive at your final output. So actually in both cases, what you are actually doing is kind of stepwise training. It is kind of a layer-wise training. So even though we don't call it layer in this context. So for every single step, for example, in the case of a diffusion model, you will take some input conceptually, which would be the output from a previous layer, and then you will still do some reconstruction task, let's say denoising, and then you predict the output. This is how you train your model, and this is not what you do at inference time. So there is still a pretty big gap between what you are doing at training time and what you want the model to do at inference time. So then in this regard, this is just like the pre-AlexNet area in the context of generative modeling. So this is a quick summary of what I have just discussed about recognition models and generative models. This is kind of, I think this is nothing new. This is just kind of a common sense in the community. So in the case of recognition, you start from one image and then you apply many layers and you arrive at some attribute, let's say class labels or bounding box or some hidden features. And then for generation, it is the other way. It is kind of a concretization. You start from something that can be viewed as noise or that is unstructured. And then you do many steps, and then you hopefully you arrive at something that's very concrete, that's very specific. So and then these are just kind of flows of two ways. So then what I've just said can be summarized by this plot, which I borrow from Phillip. It's good to work at MIT because, well, you can borrow a lot of good stuff from your colleagues. But basically, well, this plot just that you have some data manifold, you have some embedding manifold. If you flow from your data manifold to the embedding manifold, then that is recognition, or in this context, it is representation learning. And then if you flow the other way, if you flow from some embedding or from some noise vectors to the data manifold, then it is generative modeling. So and again, this is a slide from Phillip. So it gives one very simple but concrete example of what this flow means. So here is just a very simple linear layer. You have some input vectors. You transform it by a linear matrix, and then you plus the bias, and then you obtain the output. So let's say this is just an affine transformation. So if your input is a grid, then your output will still be a grid, but it is affine transformed. But if you have some data points, which is kind of a distribution in your input space, then after this transformation, it will be flowed into another distribution. But so nothing special. This is very well known. But then it is interesting that, well, we can try to visualize the flows of different operations And you can see that, let's say, if you use ReLU, then it will flow the distribution into something that's non-linear, which is not surprising. If you use kind of a normalization, you will kind of compress your higher dimensional manifold into a lower dimensional manifold, such as a circle here. And then if you use softmax, which could be the classifier output, which could also be the self-attention operation, then you will have another form of transforming the distribution. And then, while building a neural network is just to put these many operations, that is to put these many ways of transforming a flow all together, and you hope your neural network can do a good job. And again, this is from Phillip. This is just a toy example where your input has one class which is colored by red dots, and another class which has this blue color. You want to classify it into 2 categories. And then this is how the model performs during training. And this, let's say, this is the final status of the model. And hopefully, if the model can do a good job, then all the red points will be flowed into this side, and all the blue points will be flowed on the other side, ideally. So this is just a very simple example of a classification model, or conceptually a recognition model. So then what's the implication here? So when we talk about recognition problems, usually what we care about, what we are looking for, is a flow from the data distribution or data manifold to some embedding distribution or embedding manifold. So the flow is from this way. And then usually when we talk about generative models, it is not that much difference. We just want to find a flow or learn a flow that goes from the embedding space to the data space. So it goes this way. So with this context, I'd like to talk about another work that I like a lot. That is also kind of a foundation of today's flow metric models, which is called a neural ODE. So this work was published in 2018, and basically it is a conceptual comparison with the ResNet. So this figure was taken from the original paper. The x-axis is the distribution of the activations or the hidden features. It is more or less what we have just shown in the previous figures. And the y-axis is the depth, such as the index of the neural network. And in the original ResNet, this is just a discrete update, and every single update performed by every single layer is parameterized by one neural network function. And then conceptually, neural ODE want to replace this discrete operation with a continuous operation. So basically, a neural ODE want to find some activation or some features H that can satisfy this ODE equation, which just means, well, if you view the layer index T as an analogy of time, then you can have some time derivative about how your activation changes. And you want this time derivative of the activation to satisfy this function, and this function is learned by a neural network. So then conceptually, well, there are some relations and some distinctions between these 2 ideas. So in the original ResNet, conceptually, the time is discrete because it's just the index of layer, and in neural ODE, time is continuous. And then in the original ResNet, just because, well, the time is the index of layers, you don't have a strong motivation to share the parameters across different layers. So that means usually the function will have time-dependent parameterization in the original ResNet or any feed-forward neural network. But as a comparison, in an ODE model, usually the parameterization would be shared across all time steps. And actually, in today's most popular model, the only parameters that are not shared is the time conditioning embedding. But just one more thing. But usually, even when you try to implement an ODE network, and in practice, you still need yet another neural network for you to learn this arbitrary function. And in practice, today, this is still a ResNet. So then let's come back to the bidirectional flows from recognition and to generation. So there are a lot of relations and a lot of analogies between these 2 concepts, but there is one major difference in my understanding.
So in the case of recognition, actually, usually we will have determined mapping between your data and your label. But that is, if you are given an image and if you're given a class label, then you have a pretty good idea that these 2 points in these two manifold, these two embedding spaces are connected. But this is not the case if we care about generation problem. So conceptually, there will be an infinitely large number of possibilities for us to map from the noise space to the data space. So actually, in terms of generative modeling, in terms of modeling the underlying distributions, all these possibilities are valid. So then this is the main challenge in generation model. So how can we construct this mapping? So then in my understanding, there are at least 2 different solutions to this problem. So one is known as a continuous normalizing flow, which is the original solution proposed in the original neural ODE paper. And the other one, which is more popular today, is known as flow matching, which I will talk about. So, well, actually, the term flow matching is largely due to this paper that was published about 3 years ago. But actually, interestingly, there were 3 papers that were developed independently and were posted to archive more or less at the same time at that time. So one is flow matching, the other is a rectified flow, and the third one is stochastic interpolant. So it is interesting that these 3 papers arrive at more or less the same solution, but actually their motivations and their original perspective are pretty different. So it is interesting to see that how different initial ideas converge to a similar outcome or a similar formulation. But conceptually, even though, as we may know, flow matching benefits a lot from the practice of diffusion models, but in my understanding, actually, diffusion models is a specific case of flow matching, not the other way. So I just borrowed these slides from Yaron Lippmann, who is the first author of the flow matching paper. So basically, it just says a diffusion model is a special case of flow matching, which is also a special case of flows, and which is a special case of a generative model solution. Okay, then next I will give a very quick and very brief introduction of what flow matching is doing. So basically, as we have just discussed, let's say we have some data distribution denoted as X here, and we have some noise distribution denoted as epsilon. And then what flow matching does is to do a linear interpolation between these two, and we denote the interpolated outcome as Z, which would be a position or a location between these two distributions. And then we can also define a quantity that is known as velocity, which is just the time derivative of this quantity. So taking time derivative of this equation will give us this result. So then this is known as conditional velocity because this quantity depends on X. So it is a quantity that is conditioned on X. So that means even if you are standing in the same Z, when you sample X from different points, you will still have different velocity. So at one position of Z, you will have multiple velocity, and this is actually not what we want. So what we want in reality is that we want the marginalization of all these possible velocity. Let's say if you average everything here, ideally we will have something like this. So if you write it as an equation, it can be defined as the expectation of all possible velocity in this location, and this is known as marginal velocity. And then conceptually, what flow matching wants to learn is a neural network parameterized by theta, let's say this is V theta, and it wants to learn this marginalized velocity field. So this is the original flow matching loss. So, but even though this marginal velocity exists, but in general it is unknown because it is just the average of a bunch of conditional velocities. So this is not computable. But fortunately, what is computable is that you can replace this marginal velocity with this conditional velocity. And then you can arrive at this new objective function, which is known as conditional flow matching. And this is what is actually being done. So it can be proved that these two objective functions are equivalent. So conceptually, flow matching is very simple, but it works very well. So let's say if we have got the underlying flow field, then how can we get this trajectory? So how can we find out this trajectory that links from one data point to one noise point? So conceptually, the way for us to find this trajectory is to solve this ODE equation. So what does it mean by solving an ODE equation? It means we want to find the positions of z such that the time derivative of your position will satisfy the velocity field when you try to read out from this position in that field. Then conceptually, actually in principle, this has nothing to do with your neural network. So this trajectory is determined, it is given by the ground truth velocity field. But of course, this ground truth velocity field is unknown, it is high dimensional. So in practice, we approximate it by a neural network. And also on the other hand, just because this is a differential equation, so then ideally, at least in terms of notations, what we want is a solution that should be written by integral. So that is, we want to start from a time step t, we want to arrive at another time step r. Then actually this equation just means we want to do an integration from r to t. So this is what the underlying trajectory should be. But this is not what we can do. And in practice, in today's computer, what we can do is just a bunch of finite sums. So that is, we will replace this integral just by an addition, and we will use this velocity to represent everything in this time interval. So basically, this is what is being done in flow matching. But then what's wrong here? Let's go back to our comparison between ResNet and ODE. So in the ODE framework, hopefully we want to solve this ODE equation, and in terms of notation, we want to have a form that is an integral. But unfortunately, in practice, what we are still doing is still a kind of an addition. It is just yet another finite sum. So it is just yet another ResNet. So that means we want to do ODE, but in practice, what we are still doing is just yet another ResNet. Okay, so before I move on, I just want to summarize some takeaways of what I've talked about so far. So it is interesting to see that while many of these illustrations are, well, surprisingly similar, so they are just flows between two things, from, let's say, from the data to the embedding. So recognition and generations are just flows between these two distributions. So flow matching is great. Flow matching works very well, partially because, in my understanding, it can provide some ground truth fields. Let's say this or these purple lines. It can provide some ground truth field for training. So these ground truth fields pre-exist. So they are implicit. They pre-exist. Pre-exist means if you are given a data distribution, if you are given a noise distribution, if you have defined a linear interpolation between these two distributions, then this trajectory has been there. You don't need to introduce a neural network to make the field happen. They has been there. So the job of the neural network is to learn it. So, and also, as I said, even though neural is a great idea, it wants to an ODE equation, you want to do integral, but in practice, we still do finite sum. So I'll put all this together. So we are just curious. So can we move at least one step further? So can we try to find a model that is the feed forward, that is end-to-end, that is more like the AlexNet counterparts in the case of generative models. So how can we do that? So this is a research work of my team. So it is done by Jun-Yan Zhu, who is a PhD student at CMU and who did work when visiting my team. So basically, we propose a method that is known as mean flow, and so that this model could be designed for one-step generative models. Okay, so to recap, this is what we have discussed. So we want to do integral, but in practice, we still do a finite sum. So what's the missing piece here? So conceptually, it's simple. So you just shouldn't use V to represent everything in this integral. So if we borrow the concept from physics, So V is just a velocity that should be called instantaneously velocity. It can only describe the velocity at one specific time. It can't characterize the velocity across a time interval. Instead, we need to introduce the notation which should be called average velocity in the context of physics. So it is the integral of the velocity in this time interval, and then you divide it by the time interval. Then the integrand in this integration is the original instantaneous velocity. So we want to treat this average velocity as the first class citizen in our generative model. So what does this average velocity imply? So let's say if you have some trajectory that exists, then by definition, this instantaneous velocity should be the tangent direction and should have the magnitude that equals the tangent of the trajectory. But as a comparison, and the average velocity doesn't need to follow the direction of the tangent. It depends on the starting point and the end point on the trajectory. Let's say here, if the starting point is R, the endpoint is T, then this would be the direction of the average velocity. So, and then if you time this average velocity with the time interval, then what you get is a displacement. So then what does it mean in this case? So actually, there are many good properties about this average velocity field. The first noticeable property is that it is inherently a flow field that should condition on two time variables. So one is the starting point, the other is the endpoint. There's no way to define such a variable that such a field that has only one condition variable. So here in this illustration, it just means if you want to visualize this field, you need to, let's say, you need to pick one time variable, let's say 0.5, which means the 50% in this trajectory, and then you can start to illustrate the vector field on the other point. So if you pick another point, let's say 70%, then you can have another field which would be different from the previous one. So this field is determined by two time variables. And again, just like instantaneous velocity is a ground truth field that exists that doesn't depend on neural networks, here the average velocity field is also a field that exists and that doesn't depend on neural networks. So it can provide a target for us to train a neural network, but we don't need to introduce a neural network to define what this field would be. So in order to make use of this concept to create a function that is trainable, as we have discussed, we are not able to do integrals in general in our computers. At least we can't do it in an analytical way. But what could be reasonable is to find the derivatives. So then our idea here is just to differentiate the equation. So basically, we rewrite this equation by move the time interval to the right-hand side, to the left-hand side, and then we differentiate with respect to t on both sides. But this is just high school calculus. There's nothing special, but it is still interesting to note that. So when we applied the time derivatives on the left-hand side, we will have one term that is the zero-order derivative about the function, and then we will have one term that is the first order of derivative. So it is just because we have these two terms, we will be able to have a trainable objective function. So this is what we can have on the left-hand side. Then on the right-hand side, it is very simple. It's just the definition of derivatives. So basically, it is it is just the so-called fundamental theorem of calculus. So this side will give you the instantaneous velocity. So then if we rewrite this, if we move this term to the left-hand side, we will have this equation which we refer to as the mean flow identity. So basically, this is the mean flow identity. Then on the left-hand side is the average velocity. On the right-hand side, there are two terms. There's the instantaneous velocity, and then you need to care about the intervals between these two time variables. And there is one term that's interesting, which is the time derivative of the field that you may care about. So before we move on, we need to discuss how we can compute this term. Well, actually, computing this term is easy. So notice that this is the notation of total derivative, and then you just need to expand it as a sum of partial derivatives with respect to all inputs. And then you can rewrite this in a matrix form. And actually, this first term is the so-called Jacobian matrix. It is just the first order derivative of the function that you care about. And the second term is just these three time derivatives. And in our formulation, we just view the other time step as independent of t. Then this term is 0, and this term is 1. And what's interesting is the first term. So if you want to compute the time derivative about your location, let's say about your position z, then this is exactly the ODE we are trying to solve. Then by definition, this first term is the velocity. So then with this definition, we can compute this outcome by an operation that's known as Jacobian vector product, or JVP. So in PyTorch or in JAX, this is just one line of code. So if you have a function, you have some inputs, you have a tangent vector, then this is how you can obtain this quantity. So you may not be familiar with this terminology JVP or this concept, but actually there is a related concept that you are actually using every day, which is known as vector Jacobian product, or VJP, which is actually backpropagation. So in JAX, these two operations are implemented in the same way. So then basically, well, JVP is can be implemented in a very efficient way, just like how we do backpropagation. Okay, then with this, as we have discussed, we have an equation that can relate that can relate average velocity to instantaneous velocity with some delta. And it is worth noticing that what I've talked so far has nothing to do with neural networks. So all these quantities are about the ground truth field. So this equation will give us an objective to train a neural network model. So then it's time for us to write down this objective. We introduce a neural network, let's say U theta, which is directly to parameterize the field that we care about, let's say the average velocity field. Then we need to introduce a target, and this target could be given by the right-hand side of this equation. And then this target is just this term, so I copy it here, and then it will be given by the instantaneous velocity, and then this quantity that could be computed by JVP. So very simple. But there are still some interesting properties about this formulation. So first, it is easy to show that if your neural network is perfect, if you happen to achieve 0 loss, so it can automatically satisfy the mean flow identity. So which means if you find this ideal function, it will be the average velocity of the underlying flow field by definition. So you don't need to do anything extra. So when we do this, we don't need to introduce any integral computation. What we need is only derivative, or more precisely, kind of JVP. So we can prove that these two formulations are equivalent. And then we use a stop gradient operation here following many related work. So by doing that, we can prevent higher order gradient. So that is, even though there will be some gradients in this operation, so we don't need to care about that. So the gradient in the SGD optimization is just about this model. And it is also worth mentioning that there is no way for a single time function to do a good approximation of this objective function. So that is because for the ground truth targets, there is always 2 time steps. So you always need a function that has 2 time conditions to approximate this function. Okay. Then just one more thing. So what we have just talked about is about the marginal velocity in place of the instantaneous velocity. But as we have said, the marginal velocity it exists, but it is not explicitly accessible. So we just use the same trick as in flow matching. During training, we replace this term with the conditional velocity, which is computable. So then at this point, everything is computable. We just need to train this model. Just one more thing, which is also an interesting part of this work. We can show that we can address CFG, classifier-free guidance, in a similar way. So we just conceptually CFG are just two flow fields. You need to define two flow fields that exist, and then you define an interpolation between these two fields, and then you just need to replace this term with this equation, and then we can do CFG at training time. So you don't need to introduce any extra computation at inference time. Okay, so with this, so this is the pseudocode of mean flow. So conceptually, it's very simple. So it is not too much different from the original flow matching. So basically, you will have a network function to model the velocity you care about. You sample a batch X, you sample some time steps, you sample some noise, and then you do the linear interpolation. You compute the instantaneous velocity.
But I can tell you the main idea
that you
of
need
mean
to do is
flow.
to do this
Basically, for
computation, which will
rectified
give
flow,
you the
we
time
predict
derivative.
kind of
And then you
the
modify your
velocity
regression
step
target
of the trajectory.
that is
It is
determined by this time
instantaneous
derivative.
velocity.
And everything else is
But for
exactly
mean
the same
flow,
as the
you
original
want to
flow
learn
matching.
to predict how
And with
how
this definition, sampling
much
with mean
you
flow is
pass.
also simple.
So
So as
when
we
you
have
go from
discussed,
one
what we
point to
want
the
is
other,
this integral. So then we can
so you
safely
have this
replace it
trajectory,
with the
and then
average
you
velocity
take two
because,
time
well,
steps.
this is just
So
the
you want to go
definition.
from this time step
And
to this
then,
time step, and
let's say
then
if you want to
predict
go
the average
from the
velocity
starting point to the end point, or
across
actually
this.
at sampling time, it is go from the end point to the starting point.
Yeah,
You just
so
need to
they
perform
take
this
this
function
rectified
where
flow
your
equation,
time
then
step
they
t
do
is 1,
some
which is the end point, and time
algebra
step
and
r is 0,
calculus
which is
tricks,
the starting point. So,
and
very
then
easy.
they arrive to some formulation.
So here are just some experimental
which is
results. Here
manageable
we
to
compare
calculate.
the
And
one-step
it involves
generation results
some
on the very challenging ImageNet data set. So we compare 4 models from a base size to an extra large size. So we compare training with different number of epochs. So basically the model is very stable. It is very scalable. It can enjoy the benefits of going larger and training longer. And then we also compare it with some very recent related work on few step generative models. So if we care about one NFV generation, so our result is about 7% better than the previous state of the art. And if we care about 2 NFV generation, and our method is yet another 7% improvement. So we also compare our method with other family of methods, and the most interesting ones would be the diffusion models, let's say DIT, which is a diffusion a model based on transformers, and SIT, which is the flow matching counterpart. So this table just shows that while our 2-step generation results are already very close to these many-step generation results of this very strong baseline. So basically, we have largely narrowed the gap between multi-step generation and 1 or 2-step generation. So here are some quantitative results. So well, these results are, of course, not perfect, as can be reflected by the FID number. So the FID number of this image is at 3.4. It still has some gap from the state of the art, but it looks like the model is doing a pretty decent job. It can generate a lot of details and high-level structures. So all these are just 1-step generation. Okay, and well, our work is related to many efforts that is being done in the community, including consistent models and some other models that are also conceptually two-time variable models. So including, let's say, consistent trajectory models, flow map matching, shortcut models, and inductive moment matching. And our method is also conceptually related to normalizing flow, and recently there is a strong interest in revisiting or maybe reviving normalizing flows. And there will be another talk today, I think, in the afternoon, that is about this direction. Okay, so basically, this is the conclusion of this talk. So the interesting question here, in my understanding, is that, well, even though the generative models are very good today, but it looks like we are still in the pre-AlexNet area in this context. So that is, we have an inference time computational graph, but we don't respect this computational graph at training time. So we are still doing kind of a layer-wise training for our generative models. So we propose the mean flow algorithm, which hope to move one step forward. But conceptually, still, mean flow is still driven by the iterative flow matching algorithm or its diffusion counterpart. So conceptually, the mean flow network are still playing two roles. So one is to construct the noise to data trajectory. So this trajectory pre-exists, but they're not known. So the neural network still need to play this role to find them. And then at the same time, the neural network needs to summarize this underlying field by introducing some coarsening time steps. So moving forward, I would like to see a framework, an end-to-end framework that is just like the paradigm shift from the pre-AlexNet area to the AlexNet area. That is, hopefully we will be given some inputs of your neural network, and your neural network will do some transformation, and you will have some outputs, and then you will define a loss function that can evaluate how good the output is, and then you do backpropagation. So ideally, that is the spirit of end-to-end training. So how far are we from that goal? It is still unclear, and I hope we can pay some attention to this problem. And with that, this concludes my talk, and I'd like to thank you for your attention.
So now we're having the final talk of this morning session, but let me try to figure out how do I do it. It will from Robin Rombach, the author of Latent Diffusion and Processability AI. I will need to figure out. Hi, Robin, can you hear me?
Hey, yeah, I can hear you. Can you hear me?
Let me try to figure out how can I make you speak in the room, because the audio is not connected.
Oh no. I'll try sharing my screen in the meantime.
Yeah. Robin, can you speak now?
Yeah. Hi, can you hear me?
Hi.
Does it work? Hello? Can you hear me? I need to get some signal on whether you can hear me or not.
Oh yeah. So sorry, I'm muted. So it's fine. So can you say something and we can test the microphone?
Yeah. Hi. Nice to be here.
Okay. Okay. Cool.
Works.
So,
okay. Cool. Let me find
okay. I think now it works. So can you share your screen?
Yeah. One sec. Let's try this for now. Cool. Can you see that?
Yes. Great.
Okay, great. Cool. Do you want me to get started? Are you ready?
Yeah, we are ready. So
okay, cool. Yeah. Thank you. Yeah, welcome everyone. It's a bit weird talking into a void. I literally see nothing, but let's try it. Too bad I can't be there today. But yeah, we'll actually fly to CVPR tomorrow. Yeah, the title of my talk, What's After Diffusion, or like in spirit of this workshop. And my answer to this is, I don't know. Like this gentleman here with the 3 hands. But I have, I think, some ideas of what currently is going well, what are interesting directions, and what could be like future directions of development in diffusion, modeling, distillation, and etc. And yeah, I just wanted to briefly give like an overview of, I think, the directions and works that are currently looking very interesting and nice, and then also conceptually of like where model development might be headed from like a capability perspective, etc. So why would you actually think that you need to further improve? I mean, you can generate extremely realistic images now. This is one that I generated with Flux. You can make like very messy bedrooms, or with the VO3 recently, very nice videos. I didn't add the audio, but yeah, it also added that capability. And yeah, both of these, like the image generation and the video generation, they use latent diffusion. This is like an excerpt from their tech report that Google published. And so you might ask yourself, so why do you actually need to go further? Then aren't we done? Do we just need to scale the data and we're good? And I would argue that yeah, it's not really true, because one of the main problems is that diffusion models, as we know, are kind of slow when you use them in the vanilla formulation, and they are also slow to train. So you have to spend a lot of training compute to actually make them converge. And there's a few works that basically try to tackle this, both like on actually architecture of the model, on training strategies. I'll talk about the training strategies a bit, the choice of the documentation, and how to make these models faster, both during training and inference. And then, yeah, the second part, I want to focus on kind of the stuff that is more of an application of diffusion models, like what could be interesting tasks that diffusion models can solve or should be able to solve in the future. And yeah, when I say diffusion, I mean diffusion and flow matching equivalently, just to put that as a disclaimer. So yeah, let's look at some research that is trying to accelerate the convergence and also making models better. And before we do that, I just quickly wanted to give like an overview of like the very rough components of a modern latent diffusion model. Can be for images, can be for audio, can be for video, where you basically in the flow matching formulation try to match a target velocity, and you usually encode your data with some encoder, some autoencoder, which is the E-phi here in this formulation. And I note these down because we will look at all of these parts here individually. In general, denoising is like this very, in my intuition, a very broad, very general objective that is very powerful, very expressive. But as we have seen from like practice, it sometimes needs a little push into like the right direction, right? So this is true of both inference, where you know that you can sample a model with classifier-free guidance, for example, to make it to make the samples crisper, but also for training, where we have seen like actually the success of diffusion models initially when they were introduced in DDPM was that they introduced this reweighting of the loss over the different time steps, the kind of famous L-simple objective from DDPM. And that's like, yeah, one of their features is that they really allow like this reweighting of perceptually more or less relevant steps to accelerate the convergence of the model. And that simple trick was actually, in my opinion, what made diffusion models initially like really take off. We've seen that in the past, that you can influence this in very different ways. This is one of our works that we had published 1.5 years ago, where we did not reweight the loss explicitly, but the time steps that are being sampled during training. And in a similar way, when you focus on like intermediate time steps that are perceptually relevant with some parameterization of the distribution that you sample these time steps from, you can accelerate and improve the convergence of these models quite a bit. However, there's also some other ways of improving the models. One of them, or one like general class of approaches, I would say, is expanding the feature space on which you're trying to denoise, which you're trying to match with your model. And the motivation behind this is usually to focus the model on modeling structure or motion explicitly, rather than implicitly only by matching RGB pixels. And some examples that I want to talk about are Video Jam, paper that was published this year, and Red Eye. And we'll talk about both. First, Video Jam. This architecture looks kind of complicated, but is fairly straightforward, and the approach is also generalizable. Video Jam was introduced to improve the motion in video generation with diffusion models. And kind of the trick here is to use the second representation, which in this case is optical flow, estimated from an off-the-shelf network, that you also encode or represent first in RGB space. You can use the same encoder to encode these flow maps into latent space, and then you basically just concatenate these features to your RGB pixel latents and denoise this jointly. And that's a fairly straightforward trick, but has been shown to improve the performance. It also enables you to do some kind of more interesting guidance at inference time. So this paper introduced something that's called inner guidance, where when you're interested in the end in synthesizing good RGB outputs, you can use the intermediate predicted flow map as a way to guide the model. And this can be generalized to any type of spatial representation, I would say. So, for example, you could replace the flow estimation with monocular depth, or maybe semantic maps, or whatever kind of representation you have. And it's extremely straightforward if you then represent that data in RGB space and just use the same encoder that you use for your actual pixel data. Another approach, which is in the same class, I would say, is to not use representations that you would visualize, or representations in RGB space, but more abstract representations that you can still concatenate to your latent sequence. So in this paper here, they used Dino V2 features, or more specifically, PCA run over the Dino V2 features, so lower dimensional representation, concatenated that to the VAE latents, and then jointly diffuse that or denoise that with the standard DIT architecture. And you can play a little bit with like how you weigh this additional denoising target, but ultimately it means just like concatenating new features that are that give you some high-level structural information, and that process overall seems to really help and accelerate the diffusion training. These are like two works or lines of work that have been shown to be promising this year. I think like the open question here is like what other representations might be helpful. If you think about text-to-image generation, for example, you might want to align with, or you might want to denoise features that are more aligned with textual representation. And maybe there's also some other interesting representations for other data modalities. There is, I would say, a type B of this like alignment with higher level features, which is more explicit in the sense that they add like a additional loss term to the objective. So you have your classic denoising objective, and then you add an explicit regression loss, explicit similarity that you want to maximize on some features. So a very prominent example here that is gaining a lot of traction as REPA. This has been, and I'll show the results in a second, has been proven to accelerate convergence quite a bit of diffusion models. And the idea is or the motivation is very similar to what I've just shown before with the concatenation approach, is to just align the model with some high-level features. And how you do that in practice is you have your diffusion transformer, and at a certain layer, which is a hyperparameter, you add a small trainable MLP, which basically extracts the features from that layer, and then the additional loss term encourages the model to align this with some off-the-shelf pre-trained visual encoder features. And that is oftentimes Dino again. And as you can see here in this plot on the right, this really dramatically accelerates convergence of the model. However, this isn't like completely free lunch. There is this really nice work that popped out recently. It was released recently, which is called REPA Works Until It Doesn't. So yeah, very telling title. And it basically says that, yes, this helps initially to kind of accelerate the convergence, to make the model focus on like high-level features more early. But then at a certain training stage, it stops being helpful. And after that training stage, these two losses might actually counteract each other. And the very simple solution to that is just do early stopping on the REPA loss, which I think makes a lot of sense. And then just continue with diffusion training. And the hypothesis is that you, at this point, would still be in a better optimum than you would have without that REPA alignment. And as another benefit, you would still get the accelerated training. And they propose like a nice metric on how to kind of track this this counteraction or this potential fighting of the two losses, which is basically just the cosine similarity between these two different loss components or their gradients. And yeah, there's very similar to the concatenation case. There's like some open questions as well. One is, which is kind of unanswered, does scaling these representations help? In the original REPA paper, they try to not only align with Dino, I think Dino V2B features, but like different larger versions of the model and also different models. The scaling trends there haven't been as clear as you would expect, which is maybe kind of a hint into the direction of what the previous paper I was just talking about explored, that this additional alignment can only give you like limited expressivity, but at a certain point it actually hinders the full expressivity of the model, and you might actually bias in a certain direction. The second open question in this is, yeah, can you also use like some modality aligned representations? So how does REPA for video look like? Canonical approach would be to use some video encoder that has like a holistic understanding across the temporal dimension, or if you actually, I don't know, are interested in also outputting text, can you use some text features? Cool. So there's that's basically the loss component. There's also the latent space component, which is something that is also picking up, has surprisingly hasn't really been touched in the past, but is now gaining a lot of research interest actually. And in a nutshell, this means let's try to find a better latent space that is more suitable for actually training a diffusion model on it. Main idea of like the two first papers that I want to quickly talk about here is that if you shift or rotate an input image, that should actually in the latent space result in some predictable and smooth changes. In practice, that isn't the case with most of the off-the-shelf encoders, which has kind of been has been discovered in the last few months. But these simple hacks, these simple modifications, they really help fixing that problem. And the intuition behind this predictability of latent space changes is that it should allow for easier diffusion or flow matching modeling. There's two papers that I picked for a quick highlight here. One is the improving the diffusibility of autoencoders with very telling title, which shows that if you actually do employ an equivariant condition on the latent space, that helps the diffusion or like the overall generative performance as measured by FID here on the left side. On the right side, a very similar approach, which visualizes the latent codes after that additional regularization. And as you can see, if you compare it to like classic stable diffusion or STXL VAE, you see that these latents are significantly smoother, less noisy, which intuitively and in practice helps to learn or easier learn a diffusion model on them. And then there's one approach I also quickly want to talk about, which kind of puts all of this together, which is called REPA-E. And this is one of the first more promising end-to-end style approaches. So what this does is it uses REPA, and it has the additional intuition that the simplest way of how you could basically improve the diffusibility of your latent space should be by training your autoencoder jointly with the diffusion model. That has been tried in the past quite a few times. It doesn't work that well. It's super tricky to stabilize and to balance these two losses. But what they do is that they basically use REPA, the feature alignment, as an intermediate step, and they align. I'll just go to the next slide. They introduce a REPA loss that aligns the autoencoder features with the diffusion model features. It's kind of this intermediate layer here in between. And if you do that, you actually, as you can see in the plot on the top right, you actually end up with significantly increased convergence speed. This is something that I find really promising. You can also just decide to turn off that REPA alignment again at a certain stage. You can also treat that that VAE after you have done this alignment training as just an off-the-shelf VAE and train different diffusion models on them. In fact, the authors of this paper, they have released a REPA-E aligned version of the stable diffusion autoencoder. And you can use different diffusion models, different transformers as the backbone, and you actually consistently see improved performance on this. So that is actually quite promising. Cool. So this is mostly about training, and as we have seen, you can dramatically accelerate convergence speed to reach a certain image quality level. Here, factors 17 to 45. However, the second big part, which has been discussed already, I just saw the last few minutes of the prior talk, is the inference, where like the natural extension of what comes after diffusion is usually a distillational approach. But and I'll keep this short because we've just seen this actually. you can also try to directly train a few-step model. I wanted to very quickly highlight this paper, which we've just seen in the presentation. Mean flows, I think, is a super promising approach because it defines an objective that directly enables few-step inference if you correctly match it. And this is by construction of this objective, which makes it super beautiful. And the objective is actually very straightforward to implement, as you can see in the pseudocode. So I'm quite optimistic that we will see more of these types of models in the future. Some other nice works that also evaluate the model on multiple time steps, which is essentially what this method is also doing. I quickly wanted to highlight our inductive moment matching and shortcut models, just as a reference if someone is interested. However, I'm also a big fan of something that's called adversarial diffusion distillation, which our lab has been working on for quite a while, and is kind of an alternative to these direct few-step approaches. It's more of an, I would say, iterative approach, because you usually start with a pre-trained diffusion, like multi-step diffusion model, and then distill this down to a few-step model, and to fix kind of the artifacts that are being introduced by this process, you employ an additional discriminator that maps these generated samples to the real image manifold. And you can do that because with a few-step model, you can actually evaluate that in the training. It's not too expensive, and this has been a process that in the past has worked quite well. Like combining a general likelihood-based model with a more localized discriminator. It's actually also what drives the success of latent diffusion overall. If you zoom out from a very high level picture, these things look somewhat similar. So just a very quick recap on how that works. And this first approach, it was like a diffusion distillation in pixel space, super inefficient actually, and inflexible because it used an off-the-shelf encoder, was kind of fixed to 508 or so squared pixels, didn't support multi-aspect, and that also made it not really scalable because you always had to decode to pixel space. But the approach that now works and is very general and scalable, in my opinion, is what we call latent adversarial diffusion distillation. And I think the beauty of this approach is that you basically reuse your pre-trained teacher model, both as an init for your student model, but also as a discriminator. And that really makes it work on, like, you don't have to think about the aspect ratios, the resolution, the data structure, because if you have trained the diffusion model on that data, you typically would expect that you can also train a latent adversarial diffusion distillation based on this architecture, because it all operates on a sequence. And this also, because you avoid like this decoding into pixel space, makes the distillation of much larger models possible. And the second advantage of actually incorporating adversarial training in this distillation process is that you can tune the quality diversity trade-off. So typically what you have is that adversarial training reduces the diversity of the samples a little bit. But since you're actually training, or since you can train if you want to on real data, you can actually go beyond the capabilities of the teacher model in terms of, let's say, realism, raw pixel performance. And it's something that, we can see in this plot here, where for the same prompt, for this cool-looking priest pig, we got much more variance diversity when we sampled this with the teacher. In this case, here, this was very old SDXL. But you get crisper samples with a reduced diversity when you do this with the adversarially distilled model. And yeah, I talked about this already, mentioned briefly, just as a recap. That's why I like this adversarial approach, because in my opinion, it really summarizes the mode covering, or it brings together like the mode covering aspects of like general purpose, like US-based models, also diffusion models, with the mode seeking behavior of adversarial models. And training these models from scratch doesn't really work. But if you have a nice init, if you actually can use the teacher also as a backbone for your discriminator, that is something that seems to work really well. All right. This was like a bit of an overview of like all things on the algorithmic side. Let's shift gears a little bit and look at capabilities of the models. So what could be beyond, I know there's much more than text-to-image diffusion. It's kind of like a standard use case that everybody keeps coming back to, keeps referring to, but I think we're actually now at a point in model capabilities that we can really go beyond this. So quickly want to talk about this. As a quick motivation, I'll try to generate an image of a gull wearing virtual reality goggles. If we do that, we get a nice gull, text to image, works well. But now let's try to actually make this an upper body portrait. And even if you use the same seed, you know that there's no consistency. If we just do text to image, we basically go back to nothing. It's really hard to kind of get the same sample where we only modify the part of the prompt that we actually wanted to. So there's no consistency between pure text to image generations by construction, which is like one of the core problems with pure text to image models, which reduces usability, applicability in quite a few cases. But yeah, let's just say, okay, the sample here that we arrived at is actually nice. Let's keep that. Next question is, this is a sample from the model. I don't know, I might have to take like hundreds of sampling approaches before I arrive at something. It's somewhere hidden in the latent space, basically. But how can I keep this character, this specific thing, which didn't exist before, and basically add knowledge about this character into my model? I mean, it's something that is like a huge topic. Fine-tuning on a few examples, retrieval augmentation, all this stuff has been tried in the past already. And it works to a certain degree, but it also breaks really quickly. And ideally, we would like to have a model that can do that for any type of real or generated input. It doesn't even have to come from the same model. It could be like some different model. So we really want to have like the ability to basically adjust the model at inference time to any kind of visual input that we give it. And that's something where we put out a model recently that does a first step at solving that. That's a model that we call Flux One Context. Basically does in-context image generation and editing. We can now take this model, use this example of this generated character here of this gull, and put it into like very different contexts just based on the text prompt and on this input image. And we now are actually able to retain the identity and the objects, and still like very flexible in how we modify the images based on context. And this model is remarkably simple. It is a pure flow matching model. We basically just concatenate the sequences of the data and the conditioning. The conditioning in this case is text, and also the representations of the context images. And then just put it through a standard diffusion transformer architecture, in this case, the Flux One architecture, and decode with the VAE to pixel space. And I think it's really nice that such a simple diffusion-based approach actually works. Another example here, we can start with this image and say remove the thing from her face. It does that. We can now put her into the streets of Freiburg taking a selfie. That works too. The identity is retained. We can now make it snow. That also works. another application of these kind of models that I find really nice and which has potential in product photography everywhere is you take an input image. We can extract part of the image, in this case the skirt. Prompt is here extract only a skirt over white background. And then we can go further based on that image and for example, show an extreme close-up. This also shows like this iterative application of the model. There's some other in the wild examples of how companies are using this. One I find quite funny is this cleanup app. Another one was recently launched by this company Higgsfield, a really nice video editor that also uses the character consistency of flux context in the background. And maybe to kind of assess like the capabilities of that model a little bit more and to compare it to an autoregressive model, which GPT image 1 is, you see that you are able across like multiple edits. By the way, this is Dustin from our team, who is kind of the visionary behind this model. You see that you're able to retain the identity of that person in the input image. And with a lot of other models, this kind of drifts over multiple edit turns over time. You can actually verify this by calculating an all-face similarity score across these edits. And evaluate this on other tasks as well. It's not only about like face editing, so you can do text editing, localized editing, more global editing, and the character reference that I talked about. And overall, this, again, I think remarkably simple approach works quite well and also outperforms autoregressive approaches. And the other upside of that is it's a diffusion or flow-based approach, which really enables fast inference of the model and enables to serve this efficiently. There's a few failure cases still of these models, which I think are very interesting directions to work on in the future. One is over multiple turns of editing, you end up introducing degradations in the outputs. Ideally, you would want to have the ability to infinitely edit images, right? Something that currently doesn't work. And I think it's interesting to think about how to fix that. Another more obvious one is sometimes model just doesn't listen to the prompt that well. So we wanted to move the coffee to the left, and I don't know, it just added some milk foam, but didn't do anything else, which is clearly not what we wanted. There's a more general like prompt adherence thing, which might be solved by more scale, but maybe there's also more elaborate methods. And another one, which I think is mostly a data question, is that sometimes, or like most often, the model works really well in like the ability to retain input characters and listen to the text prompt. But sometimes there's this failure mode of where you modify more than you actually wanted to, and you have like global changes in the image. For example, this identity of this woman here is changing, where you actually don't want that. And that's obviously also a failure mode, which you want to avoid. I think also interesting to kind of get the model like more accurate, more precise. Cool. And then some other beyond text to image diffusion topics that I think are really promising for the future. One is multimodality, mostly in the sense right now of combining audio, video, and text. After watching a few VO3 outputs with audio, and I'm sorry I didn't edit here because it usually doesn't work in presentations, at least when I give them, then you basically don't want to go back to listen to synthesized people without audio. There's a paper online called Audio, which I find really nice, and which goes in the direction of how can we do like this multimodal joint training. It actually resembles like again, from a very high level, like this concat approach that we talked about earlier to a certain degree. Seems to be scalable. Another one which might be something worth exploring and combining with this is maybe combining or starting from pre-trained pure text diffusion models, which are also gaining capabilities recently, or combining text diffusion with pixel diffusion. Then another topic which I find personally extremely interesting and promising is basically 3D scene generation, world generation in real time. This is a demo from Google's Genie 2. And this basically is a model which you can control with your keyboard. So walk through synthesized worlds. Now, the disclaimer here is the samples in this blog post are generated by an understood-based model to show what is possible, which means this is not real time. But I think, going there, actually having like a very general video model where you can take like any image, where you just put that into it, make it playable, seems to me like a very attractive direction of research and development. And the second part here is, I think, equip these models. How do we equip these models with an understanding of that the world is actually 3D? So how do we enable these models to actually do a 360 turn, and that we end up at the same place where we started? And these questions, I think that's an open question. There's some startups working on this in terms of products. I'm really curious what comes out of that. And then finally, which keeps popping back up again and again, is kind of this latent debate. Do we actually need two-stage training, or can we do everything end to end? The REPA-E paper points into the direction that it might be possible to do it. Again, it's not like this is a combination of a lot of different losses, so maybe also not what you would expect to be like the final solution. There's other works that do this based on normalizing flows or on diffusion autoencoders, or actually just develop completely new autoencoder approaches based on diffusion models. Seems to me also like an interesting direction of research. I'm curious how this will turn out. That was it from my side. Thanks. If you want to, you're more than invited to come to our small party on Saturday. Please take a picture of this one. And thank you for your attention.
Thank you, Robin. So that concludes our morning session. Our afternoon session will start at 12. Oh, sorry, we'll start at 2 o'clock. So now let's hear. Thanks, Robin.
Thank you.
Thanks.
Thank you.